All right. So in this video, we are going to discuss the Lagrangian formulation of the classical electrodynamics. We are going to consider the classical relativistic theory of electrodynamics, and we would like to understand how the Maxwell's equations arises out of a Lagrangian formulation. Okay. So before I go into electrodynamics, let me consider a relatively simpler case, which is the classical field theory of a scalar field, where by the word scalar, I mean that I have one degree of freedom, which is a field degree of freedom. That means it takes different values at different points in space-time, but it is a scalar in the sense that it does not transform under Lorentz transformation. So it's invariant under Lorentz transformation. Okay. So that is the theory of a single scalar field. That is what I'm going to start the discussion with, because it's just a simpler example of a classical field theory. And so after that, I will go into the discussion of electrodynamics. Okay. But again, even before going into field theory, let me consider let us recall the Lagrangian formulation of a simple harmonic oscillator. Okay, so as you know that the Lagrangian formulation is based on the idea of this extremization of this action. Okay, so basically we write down an action and which is a functional of the degree of freedom, which in this case is x as a function of time. Okay. And we write down the corresponding Lagrangian. The action is written as a time integral of the corresponding Lagrangian, and the Lagrangian is given as the kinetic energy minus the potential energy for the harmonic oscillator. The kinetic energy is half mv square, as you can see, and this is the potential energy. And we have to remember that this x of t, this function is the function which is the degree of freedom here. Okay, so we would like to find solutions which are x as a function of t. We would like to find solutions which extremize this action. Okay, or if you like, maximize the action. So that is the action principle. But because this is the functional, so we have to perform a functional variation of the action to extremize it. And that functional variation would give rise to the equation of motion, which we can then solve and find the solution for this problem. Okay, so that is the idea. And so how do we do the variation? So if we have this functional, we vary the action with respect to this function x of t. And so if we do the variation goes and it can hit the x of t function. So for this term, it is simple. It just gives me twice x delta x for this term. And for the first term, there are time derivatives. So it can either act on the first time derivative, this one, and or this one, because it's like whole square. And that gives me a factor of 2, which cancels this half here. And so the first one remains. This is the velocity. And the second, this is multiplied by the time derivative of the functional variation of x. Okay, so so basically this is the thing. This is the variation of the action, and then what we do usually is we do an integration by parts on this term, and take this time derivative and put it on the rest. So basically we can write this as a total derivative minus this term, and as you can see, when the time derivative here hits this factor, then I get this additional term which is cancelled from here, and when the time derivative hits this variation here, we get back this term. So this is just an identity that we use to write it in this way, and we have done this many times in our previous discussions. And so once we do that, then this becomes a total derivative, right? And total derivatives, as we know, are given by the endpoint. So if we integrate this, then this is basically going to be given by whatever occurs inside, evaluated at the endpoints of this integral, right? And that term vanishes if we say that this variation vanishes at the endpoints. Okay, so if you do perform the variation keeping the endpoints fixed, then this variation vanishes at the endpoints, and what we get is we can forget about this total derivative term. Okay, and then we are left with these two terms here, and these two terms can be grouped in a way where there's something multiplying the variation delta x. So the whole point of performing this integration by parts or taking this derivative onto this is basically, we want to write the variation of the action in this form, that it is an integral over something times the variation in the function. Okay, so if we are able to do that, then for extremization we have to set the variation of the action to 0. And if this has to be 0 for an arbitrary variation delta x, then it must be that this coefficient vanishes locally at every point in time, and this gives us the equation of motion for the harmonic oscillator. Okay, so this was a quick recap of something that we have seen a lot of times, but many of you are in the habit of using the Euler-Lagrange equation. Given the Lagrangian, you use the Euler-Lagrange equation to write down the equation of motion. But this procedure, I would highly recommend all of you to go through this procedure, because this is much simpler. It's just taking a derivative on here, inside here. So this variation is essentially like taking a derivative, as you can see. And this is a very simpler procedure, and you don't have to remember your Euler-Lagrange equation if you perform your variation in this way and find the answer. And believe it or not, there are many advantages of doing it in this way. Okay, so it's much more simpler than using the formula, particularly when the Lagrangians are sufficiently complicated. Then this is much more easier. Okay. So this procedure is highly recommended. That is why I didn't write down the Euler-Lagrange's equation directly and find the equation of motion, but this is the procedure that is followed. Okay, so right. So now, so this is something you are all familiar with, and now what I want to go or discuss, now what I want to discuss is this scalar field. Okay. As I said, by scalar field, I mean something which does not transform under Lorentz transformation, but it's a field. So it depends not only on time, but also on spatial coordinates. Okay, so x, y, and z are the spatial coordinates. So it's a field. Okay, so this is very similar to the electric and magnetic field or the potentials that you've seen so far. And so this is the kind of thing that we are interested in. But in electrodynamics, essentially all the electric and magnetic fields and the potentials, as we have seen, they transform non-trivially under Lorentz transformation. But this one that we are considering, this field theory, is sufficiently simpler than electrodynamics. So the dynamics of this scalar field phi is going to be considerably simpler than electrodynamics. Okay, so that is why we are starting with this, just to introduce the notion of field theory and the Lagrangians for field theory. Okay, so that may be unfamiliar to some of you, that how to write down Lagrangians for field theory. So this point of discussion is to introduce that idea. Okay, so very good. So now what we have to do is we have to write down an action which is a functional of this multivariable function phi. So the function phi is a multivariable function. Apart from time dynamics, it can also vary non-trivially over space. So it varies over space and time. So phi is a function over space and time, and the action is a functional of this multivariable function. Okay. So now, given that, given that is the case, we write down the action not only as a time integral but also as a space integral of some Lagrangian density. Now, I'm calling this density because if you perform this space integral, then you will land up with something which is the Lagrangian, equivalent to the Lagrangian. So this is Lagrangian density, and as you have seen many times in the discussion of field theory, it is convenient to talk about densities rather than the integrated version. Okay, so this basically, why do I take the action of this form and perform and try to perform this variation principle? Basically, what we want is a local theory and local equations of motion for the scalar field phi. Okay. So basically, that would be possible if we essentially have this procedure of extremizing the action, and we are able to write down a Lagrangian density instead of some integrated Lagrangian. Okay, so if we have written down a Lagrangian density, then it is possible to write down an equation of motion which are valid at every point in space and time. Okay, so that idea of that is what I'm calling locality, that is equation of motion, which is a differential equation, a partial differential equation, which is valid at every point in space and time, and that can be obtained only when we write down a Lagrangian density and perform the variation. Okay. So the idea is very similar to what we have seen for the harmonic oscillator, for instance. We now have to write down, given any theory, or somebody will tell us what this Lagrangian is for the scalar field, and given that, we have to perform a functional variation to get the equation of motion, and then we solve the equation of motion, which will now be a partial differential equation, and once we solve it, we'll get the solutions which extremizes the action. Okay, so basically that is the process. And the first takeaway message is that instead of Lagrangians, we now start talking about Lagrangian densities. Okay, and this integral is a space-time integral, which we are going to denote by d4x instead of a d cube x. Okay, d cube x dtx. So this is the whole thing we are going to refer to as d4x. Okay, so that's the first takeaway. Now, as you can see here, what I have written is this Lagrangian can be a function of the scalar field phi as well as its derivatives, right? So as we have seen here, for the harmonic oscillator, the Lagrangian here is a function of the degree of freedom, which is x, and its derivatives. Okay, in this case, there's just one time, it's a function of one variable time, so it depends on the time derivatives. Okay, so in general, the Lagrangian density can depend on the derivatives of the scalar field. Okay, it can be a time derivative as well as space derivative. But I'm not writing these derivatives separately like this. Okay, I'm not writing this separately like this, and I'm writing the four gradient of the scalar field. Okay, that is because I would want a theory of the scalar field which is relativistically covariant. Okay, so in order to ensure that I have relativistic covariance, I cannot treat the space and time derivatives separately. They have to come together to form a nice quantity under Lorentz transformation. And as we all know, that this quantity, del mu of phi, or this four gradient of the scalar field, that has nice transformation properties. It transforms as a covector. So that is the reason why whenever the derivatives appear, they must appear in this combination, okay, rather than appearing differently. So if I write down a Lagrangian, which is, let's say, del t of phi whole square plus del x of phi, this thing is not going to be invariant under relativistic transformations, okay, because space and time, when it gets mixed up, it's not going to be invariant, okay. So for getting a covariant equation of motion, we have to write down a Lagrangian which is invariant under relativistic transformations. Okay, so in order to ensure that, that is already a lot of constraints on the Lagrangian. Okay, otherwise we could have written down several different kind of Lagrangian densities. Okay, depending on various derivatives and various functions of phi, we could have done that. But because we want relativistic covariance, therefore we want the Lagrangian density to be invariant under the Lorentz transformation. Okay, so to ensure relativistic covariance of the equation of motion, we want the Lagrangian density to be invariant. Okay, that's the first takeaway, that if we are talking about relativistic field theory, then the Lagrangian must be invariant under relativistic transformations. Okay, that's the next takeaway message. Now, let us say that we don't know what the dynamics of the scalar field is. So we have no idea about this L. Okay, we just know the fact that it has to be invariant under relativistic transformations. So what are the terms that we can write in this L? Okay, so the answer to that question, what I'm going to do is I'm going to think about various terms that is possible to be written down in the Lagrangian density, but I'm going to classify those terms according to the number of derivatives that exist in that term. Okay, so this is a, if you like, a classification of the terms that are possible to be written down, and that I can do based on the number of derivatives acting on the scalar field phi. Okay, so the first kind of term in that classification would be terms which doesn't have any derivatives of phi in it. Okay, so that can be any function of phi. Okay, that can be any function of phi. Okay, so before I go on, I must say that I have to emphasize this point. I was trying to motivate the existence of a Lagrangian density by the idea of locality. So even if you have this Lagrangian density and you write it this way, you can write down Lagrangian densities which are non-local. Okay, in some sense. Locality perhaps gives further constraints on this Lagrangian density, but we would like to think of. But this is more like a this is more like a case where if we have local, with some constraints, if we have this Lagrangian density, then we can write down local equations of motion. Okay, so it's not that as soon as we write down a Lagrangian density, we have a local theory. That may not be the case. Okay, so yeah, we have to be slightly careful about what we are writing here. Okay, for instance, there can be further integrals in this Lagrangian density, which will clearly make things non-local. Okay, that's what I have in mind. So very good. So right. So now coming back to this point about the classification of the terms that are possible to be written down in this Lagrangian density for the scalar field. So we have the first kind of term, which is basically it can be any function of the scalar field phi. Okay. And that function, you might try to write it in this way, that it's like a series in various powers of phi. Okay, so this is a very general form of writing down this function, and this can be an arbitrary function. Okay, that is one possibility which is allowed by Lorentz invariance. Why is this allowed by Lorentz invariance? Because phi is a scalar under Lorentz invariant. Under Lorentz transformation. So any function of phi that you write down must also be a scalar under Lorentz transformation. So we can definitely incorporate terms like this in our Lagrangian density. Okay. Now let us ask, what are the possible terms in the Lagrangian density which has just one derivative? Okay. So, I have a del mu of phi. Of course, it has to be del mu because otherwise it will not transform nicely or covariantly, as I said. So this, is it possible to write down any term in the Lagrangian density where I have a del mu of phi and just one derivative? Okay, that is not possible because I cannot make a scalar out of a vector if you don't give me another derivative, okay, to contract. I need another index to contract this vector index. Otherwise, it is not going to be a scalar. Okay, this object will continue to be a vector no matter what you do with it. You multiply it with some function of phi or whatever you do with it. It's going to continue to be to transform like a vector or a covector, and therefore this cannot be incorporated into the Lagrangian density. So there cannot be any terms in the Lagrangian density which has just one derivative in it, and this is ruled out just from the fact that we want relativistic invariance of the Lagrangian density. See how powerful it is. Okay, so we are already ruling out a lot of terms like this when we say there cannot be terms like one derivative. Okay, now at the two derivative level, okay, at the two derivative level, there can be many terms if we allowed as I said, if we allowed for the derivatives to be separately written, like time derivative, space derivative separately, then there can be many possibilities that arises. But if we want covariance again, there isn't too much things that you can do with it. Okay, there isn't too many things you can do with it. You can either write down a term like this, which is obviously relativistically invariant because the mu indices are contracted. You can perhaps write a term like this, okay, with a single field phi. And you can perhaps write a term like phi del mu phi del mu phi, this thing. Okay, I cannot imagine any other term that you can write down at the two derivative level. Well, of course, you can convert this into some function of phi, okay, where you can, if you act the derivatives, you will get something like this multiplied by some function of phi. Okay, so in general, you can always take this term and multiply it by some functions of phi. It will still be a two derivative term. But the form of the derivatives must be of this nature that these two derivatives contract, or there's a box operator acting on phi, okay, or there's a phi del mu phi, this kind of term. Okay, so basically, if we try to write down a term which is exactly like this, then that term is going to be a total derivative term because it's del mu acting on something. And this total derivative term, as you know, even for an integral over space-time, that gives me a term which is essentially, this is a term which is a boundary term. Okay, so it's not, this term is not like a term which is present at every point in space and time, but rather it is a term which is present on the boundary of space and time. While these kind of terms can be very interesting, but in this initial discussion of classical field theory, we are going to ignore such terms. Okay, we'll say that there is no boundary dynamics and the boundary conditions of space-time are trivial. So these kind of terms are not going to exist in our discussion. Okay, so we will not incorporate boundary terms in our discussion, and therefore we will not look at terms like this, which are total derivatives. Okay. So, that is the idea why total derivatives are not written down in the Lagrangian, because they are essentially boundary terms, and these will not influence the local equation that you write down in the bulk of space-time. Okay, so these terms will not influence the local equation of motion at every point in space-time. Rather, they will care about only the boundary. Okay. So, but again, I must say that there can be some very interesting boundary effects which are very important in today's discourse. But let's not get into that complicacy right away. Okay, very good. So now, so there's a term like this and there's a term like this, which is possible to write down. So, but if we notice, then a term like this is basically equivalent to this one up to a total derivative term. Okay, how is that? Because I can take this, write it as a del mu acting on this operator. So there will be two terms where the mu acts on phi, where this will be exactly cancelled by this one. And then there's a mu act on this phi, where I'll get back this term. Now this is a total derivative. Again, for reasons that I mentioned, this is not going to be the kind of terms that we will care about. Okay, this is not going to be the kind of terms that we are going to care about. So therefore, this is going to be the this is the thing that we have already considered, and so this is equivalent to this. Okay, and again, you might say that I should also perhaps write down a term like this in the total derivative, term like this in the equation in this list. That is true, but again, this kind of term will not be considered because it is a total derivative term. Okay, this is also another possibility which is independent of this thing. Okay, so these kind of terms, total derivative terms, we are not looking at because we don't care about what is happening at the surface of space-time or at the boundary of space-time. Okay, we only care about local bulk equations in space-time. So basically, this is the term that is only there, and everything else that I can think of are essentially equivalent to this term up to boundary terms. Okay, so this is the term that is only allowed by relativistic invariance. You see how powerful it is at the two derivative level. Okay, this is the only kind of term that would be allowed by relativistic invariance. And of course, you can take this and multiply with some function of phi, which you can always do, and that is going to be the relativistically covariant, or that would lead to relativistic covariant equation of motion. Okay, so at the two derivative level, there isn't much you can do. Okay, so the form of the terms essentially gets fixed at the two derivative level. Very good. So that so that's something to remember. What about the three derivative level? Again, there is no possible terms with three derivatives because two derivatives I can contract, but the third derivative will remain free. So for the same reason why we didn't have terms with one derivatives, for those same reason I cannot have a term with three derivatives. In fact, I cannot have any relativistically invariant terms involving odd number of derivatives if we just have a single scalar field phi as the degree of freedom. Okay, so this is the, you see, how powerful this constraint of relativistic invariance is, that it throws away a lot of terms that you could have, otherwise perhaps imagined writing down. Okay, those are just not there in the description. Okay, so therefore, there are no odd derivative terms. How about four derivative terms? There are many such four derivative terms. Okay, these are some terms that I have written down. There could be more. I haven't tried to be exhaustive out here. Okay, there can also be total derivatives, which you will not care about. But essentially, these are the terms, various terms that one can, I could think of. These are the only independent terms that one can write down at the involving four derivatives. Okay, so and so on. 5 derivatives, 6 derivatives. We can just continue listing, and with growing number of derivatives, the possibilities increases. Okay, the various terms can be written down where which would be allowed by Lorentz invariance. Okay, so that happens. But here I would like to make a very important comment. Okay, the comment is that, let's say, we are looking for basically the dynamics of phi. Okay, so when phi is a dynamical field, it fluctuates both in space and time. That's what I mean by dynamics, right? So when it fluctuates, if the fluctuations are such, okay, you can think of like a wave, because you can write down any fluctuating solution in terms of sines and causes. So effectively you can it is a good you can just intuitively think of fluctuations as some kind of a wave with a frequency and a wavelength. Okay, so basically, if the fluctuations are such that the frequency and the wavelengths are long compared to some intrinsic length scale in the system, okay, then these higher derivative terms can be they're suppressed in terms of these long wavelengths. Okay, because as you can see, a derivative will bring down a factor of omega or k. Let's say phi is something of the form e to the power I omega t plus k x. Okay, of this form, then a derivative is going to bring down factors of omega or k. Okay, so the more the number of derivatives, there would be more numbers of omegas and k's, and essentially if you are in the long wavelength limit or small frequency limit, then basically these these terms would be suppressed, and basically there will be some number multiplying them, which will depend on some which can depend on some intrinsic length scale of the system. And if that wavelengths are longer than this intrinsic length scale, then you can safely approximate, or you can safely ignore these terms because they would be suppressed. Okay, because of this because of this derivative nature, higher derivative nature of these terms. Okay, so now a few comments about what can be such length scales. So of course, one thing can be the length scale up to which you can experimentally probe. So whenever you are doing an experiment on a system, which you are probably trying to model with the scalar field, let's say, there can be a length scale beyond which your apparatus that you're using to probe this system is not sensitive. Okay, so that is like a length scale of interest. So you are only interested in length scales which are longer than that length scale. Okay, so in that case, only waves that have wavelengths longer than that length scale would be relevant, and so in that case, these terms would be suppressed in terms of this ratio of the two length scales, if you like. Okay, the wavelength and this length scale, that intrinsic length scale to the problem, these terms would be suppressed. Okay, so again, when you go to the quantum version of the theory, there are some very interesting reasons, what happens to these higher derivative terms. But for the moment, I hope this point is clear that even thinking of this as a classical theory, there can be, for longer wavelength compared to some given length scale, longer wavelength for the longer wavelength fluctuations, we can safely ignore this kind of higher derivative terms, and we can work with the least number of derivatives which are there. Of course, there can be no derivatives. If there are no derivatives, then there is no dynamics. Okay. So we would at least require, the first leading order term to have some derivatives. Okay, and that in this particular case is given by the two derivative term, which is uniquely fixed. Okay, so if we say that we want relativistic invariance of the Lagrangian density, and we stick to two derivative terms, okay, which is the minimum number of derivatives, then with this idea that the higher derivative terms would be suppressed in terms of long wavelength compared to some intrinsic length scale of the problem. Okay, so in that sense, the Lagrangian gets completely fixed, right? Because then you can write down two terms like this in the Lagrangian. Okay, one term where you have a two derivative term like this multiplied by some function. Okay, this function you can put in anywhere. You can put in here, you can put in here, okay, or you can put in two different functions here, but the derivative would essentially act on the phi, because that is what is dependent on space-time, and everything, the rest will come out, and you can write down terms like this. The term, this is the most general two derivative term that you can write down. Similarly, you can add to it another arbitrary function of phi in the Lagrangian density. So essentially, these two conditions, you see, the two derivative nature of the Lagrangian density and the fact that it has to be Lorentz invariant, that fixes the dynamics of the scalar phi to a Lagrangian density, which is such a simple form. Okay, so you see the power of this idea of symmetry. So when I told you that give me any theory of a scalar field, any scalar field theory, you could have written down various derivatives and a lot of other things. Okay, but the idea that it has to be invariant under a symmetry, okay, which is Lorentz symmetry in this case, that constrains the action enormously. Okay, or the Lagrangian density is constrained enormously. In fact, here in this case, we can see it's almost like more or less fixed to this form. So again, we can find out the corresponding Euler-Lagrange equation for this general form, but let us make life a little bit simple, because this is the first one we are doing. So let's consider a simple example. Okay, let us say that we consider the Lagrangian density for which this is 1 equal to 1, okay, and this object is equal to just m square phi square. Okay, here I have called this m tilde, okay, and I have used the notation m. I'll tell you why I'm using this notation m here. Okay, why the choice of the letter m? I will tell you something about that. But before I tell you that, let us see what is the equation of motion that arises by varying the action. Now, this action is a functional of the multivariable scalar field phi. So let us try to vary this action with respect to phi. So if I do that, then you see the variation goes and hits this phi, okay, and again it can hit either this term or this term, okay. So that it cancels the factor of 2 here. That gives me a factor of 2 which cancels the half, and therefore the variation goes in inside one of these derivatives, okay, and then this m square phi square term also, there's a phi square, so when you do a variation, this gives you phi del phi, but twice phi del phi, and that too cancels this half here. Okay, so very good. Now we play the same game. We try to write this term, because you see our objective is to write something like, whatever appears inside times delta phi, that is our objective. Okay, so in order to do that, this is the term that is preventing us from doing that, because here there is a derivative of space-time acting on the variation phi. Okay, so this variation is also a function of space and time. So this can be non-trivial, and therefore the derivative can act on this on this variation as well. Okay, and so in order to take this term and write it in the form that it's something times variation of phi, what we do is we write down a total derivative first. Okay, this is the total derivative on phi, del phi. Okay, where again, when it acts on this phi, you get back this term, and when it acts on this, when it acts on this phi, you get back this term. I'm sorry, this I have written in a, this is not the correct way to write it. What I want is, when you act this on phi, this thing times delta phi. Okay, that's what I want. So when you act this phi on this delta phi, then you get back this term. And when you act this derivative on this one, then you get back this term, which is multiplied by delta phi outside the derivative. All right, so that's what I mean. And this is again a total derivative, and we are going to assume that the fluctuations, this del phi, vanishes at the space-time boundary. Okay, so so we'll assume that it goes to 0 at the spatial boundary, as well as, let's say, the initial conditions are such that it is 0, and so it vanishes in the boundary of space-time. And if that is the case, these fluctuations, if they vanish at the endpoints as well as at spatial boundary, then this term would be, you can forget about it. And if you forget about it, then you are left with these two terms here, okay, delta phi. And then you have an equation of motion, which, as you can see, is a it's a partial differential equation, because these are space-time derivatives. These are derivatives of multifunction. Phi is a multivariable function, and these are derivatives involving those multivariables. Okay, so if we write it out, so as you can identify from our previous lecture, that del mu phi, this is the box operator, the D'Alembert operator, which you can write out in this way. This is 1 over c squared, del t squared phi minus, this object, okay, plus m, this thing, m squared, m tilde squared phi, okay, that is equal to 0. This is the equation of motion, okay. The equation of motion, again, as I said, this is the variation of action, okay, delta s. And if you want to set delta s to 0, okay, for equation of motion, you have to set this delta s to 0, okay. And if this delta s has to vanish, this you do for extremization of the action. And if this has to vanish, if this delta s has to vanish for arbitrary variation phi, then this coefficient must go to 0. This is the usual logic. Okay, so this is the equation of motion for the scalar field phi. And as you can see, this function resembles very much like a wave equation. Okay, and it has this additional term, which is m squared phi. Okay, so let us say that if we plug in some kind of a wave kind of an ansatz into this equation, then so this is all I have to say. This is the equation of motion, and this is what determines the dynamics of phi. And then now you can go ahead and solve these equations. Okay, I'm pretty sure that you guys can solve this equation, because you know how to solve these kind of equations now. Okay, so given some boundary condition, you would be always you've encountered similar equation in electrodynamics, so you can try to solve this. But let us say that if we take an ansatz like a sine or a cos, this e to the power I omega t minus px, this kind of an ansatz, and plug it back into this equation, what do we get? So we get an equation like this, right? Because there's a double time derivative that brings me a I omega squared from here, and that I omega squared gives me a minus omega squared by c squared. This c squared is here, and then there's a ip squared, and the ip squared gives me a minus sign. That this sign becomes a plus sign here, and this remains m squared. And we want an equation which tells us that this thing is equal to 0. Okay, so if we take this and plug it, if we take this ansatz and plug it back into this equation, then we get back this condition, right? Then we get back this condition. Now, so if I write it down in this following form, I write omega squared p squared c squared plus m tilde squared c squared. Okay, and now if I say that my m tilde is something like m times c, okay, of course this m tilde in the Lagrangian, if you look for dimensions, then this is a dimension full quantity, of course, okay, because this is going to have some dimensions, and so this will probably determine phi will have some dimensions which will make this this whole thing dimensionless, or rather it have the dimension of the action. Okay, it wants to have the dimension of the action, and so this whole quantity, this m here would have the would have dimensions. Okay. Again, I should say that these kind of discussions are best done in natural units. And in natural units, you set all these c equal to 1, h cross equal to 1. Okay, then it's easy to count dimensions and keep track of dimensions there. But in general, this m is going to have dimensions. Okay, so if it has dimension, then I can always write it in this form, that it's, let's say, it's m tilde mc, and then I write, I can write this condition which I obtained by plugging in this ansatz in this form, which is omega squared equal to p squared c squared plus m squared c to the power 4. Okay, so this is some condition on omega and p, which is the frequency and momentum of this wave-like solution. There's a field, so in general it has certain wave-like solutions. If omega and p satisfies this condition, then it will be a solution to the equation of motion, right? But I would like to draw your attention to this expression for energy and momentum for a relativistic particle that we had seen before. Okay, so this expression for energy and momentum, which by the way, in natural units, okay, this is just energy square equal to p square plus m square. Okay, that's what you're going to write down in natural units. Okay, so so this relationship, what we have obtained here, very much resembles this relation, provided we naively identify this omega with energy and p with this momentum of a particle. Okay, I should emphasize that we are doing field theory. There is no particle here. Okay, we are doing classical field theory. There is no particle here. But the analogy, drawing an analogy with, this equation with this, particle energy momentum relation, it is, this m, or this m here, this parameter m here, is often referred to as the mass of the scalar field. Okay, I mean, there's a very concrete reason for doing that. I mean, if you do the quantum version of this theory, then you will see that there are certain particles that you can associate with the scalar field phi upon quantization, and that those particles, will appear to have a mass which is proportional to m. Okay, so that is why this term is called the mass term. Any quadratic term like this in the Lagrangian density is referred to as the mass term. But here I'm just trying to modify. I'm trying to motivate the calling it the mass term. Such quadratic terms. Calling it a mass term. I'm trying to motivate from the fact that this kind of a relation between omega and momentum, frequency and momentum, involves a term like this, which very much resembles the mass term for a particle with some energy E and momentum P. Okay, so that is the way I'm trying to motivate. But as I said, in the quantum version of this theory, this is probably more precise. But the terminology, comes from there. Okay, it descends from there. And these kind of terms, even in classical field theory, are referred to as mass of the scalar field. Although, there is no particle here. There can be only waves as long as we are doing classical field theory. Okay, I mean, there is no particle. It's always a field configuration, which is like a function over space and time. So there is no particle. Yeah. So, of course, the field configuration can be localized, etc., etc. But it's a field anyway. Okay, it's not like a particle which is moving around. Okay, so so in that sense, it is this term is the mass term, and that is all I have to say about scalar field theory. Okay, so I hope by now you have become experts in performing a variation and writing down the equation of motion. Okay, because it's super simple. This variation is nothing but differentiation in a way, and you can essentially write down the corresponding equation of motion just by performing the variation and doing an integration by parts in the terms where there are derivatives, and then throwing away the total derivative terms, and you get the equation of motion. Okay, so I want you guys to be expert in that exercise. Okay, you really want to be experts in that exercise. But here we are doing field theory. So we have a Lagrangian density on which we are performing the variation. Okay, so very good. Having understood these some of these basic points about classical field theory and its Lagrangian formulation, classical relativistic field theory. Okay, that relativistic field theory is very important because that ensures that we cannot write down arbitrary terms in the Lagrangian density. Okay, we have to ensure that the Lagrangian density is relativistically invariant. Very good. So now let us come to electrodynamics. Okay, this is our main point of discussion, and these are the equations that we have to obtain as equations of motion. Okay, so these are the Maxwell's equation. Now, as you know, and we have seen in the previous lecture also, that these terms are the terms with the sources. They are the primary Maxwell's equations. Okay, so if we consider the degree of freedom as the gauge field mu, okay, then these are the four equations for the degree of freedom mu. Okay, and the one with the sources. Whereas this other set of Maxwell's equation, they are just an identity. This conservation, this divergence of the dual field strength, they are an identity like this. These other set of Maxwell's equations just become identities. As soon as I write down the field strength in terms of this potential, I can write down a dual, and that dual, the divergence of it must be equal to 0. That is directly writing down these equations in a relativistically covariant form. Okay. Now these are the main equations which goes on to determine my gauge field. Okay, and therefore we should aim at deriving these equations, or more covariantly, these equations starting from a Lagrangian. Okay, that's the idea. Okay, so I hope the idea is clear. So the goal is to write down a Lagrangian for a degree of freedom, which now is not a scalar but a 4 vector. Okay, this is the degree of freedom. Okay, this is the fundamental degree of freedom, and with respect to this fundamental degree of freedom, we now intend to write down a theory or a Lagrangian density whose equation of motion is going to be this this Maxwell's equation. Okay, and this is the covariant version of the Maxwell's equation. Okay, so this is written in terms of the F, but as I said, if we think of the mu as the fundamental degree of freedom, then F is expressed in terms of mu in this way. And again, this is just an identity which immediately gets satisfied. And if we write down this object, del mu F mu nu, in terms of the gauge potential, the 4 vector potential, then as you can see, there's this term which becomes like the D'Alembertian acting on A, on the gauge field, on all the components. And then there's this term which is also there. Okay, but here this mu derivative you can take inside, and you can write down this as del mu mu, or the 4 divergence of the 4 potential. Okay, now as you know, and as you have seen in the previous video, that this object equal to 0 is precisely the Lorentz gauge condition, and it is also the gauge condition which is manifestly Lorentz covariant. Any other gauge condition that you put, like the Coulomb gauge condition, it is not gauge covariant. Okay, since we are doing a relativistic formulation, relativistically covariant formulation, we should also make a gauge choice or gauge condition choice which is relativistically covariant, and therefore we go on to choose the Lorentz gauge condition. If we choose the Lorentz gauge condition, then this term vanishes, okay, just by the gauge condition, and then we are left over with the equation which is basically saying that it's the D'Alembertian acting on the vector field, 4 vector field, equal to the source. Okay, so this is the equation for the this is what Maxwell's equation reduces to for the for the potentials. And as you know, we have solved this equation. We have solved this and found the retarded solutions for this equation, where we were able to invert this operator. This is like the operator which appears in the wave equation, right? If we write it out, we saw it a little while ago. Okay, so this operator, if we try to solve this equation by finding the Green's function as we did for in electrodynamics, then we simply get all the solutions, all the retarded solution that we have discussed so far. Okay, so this is just a relativistic formulation of the various solutions that we have obtained. They were already secretly relativistically covariant. Okay, and the equations were relativistically covariant, and now we have just put them together, and this is the equation that we have to solve. Okay, and we have solved this equation. We have already solved this equation, so there is no big deal. Okay, so that part is done. But now the question is, can we find such an equation of motion starting from a Lagrangian density for the 4-vector potential? Okay, that is the question. Okay, not only that, we would also like to ask that, just like we saw for the scalar field, that the condition of Lorentz invariance or Lorentz covariance restricted the Lagrangian density to a great extent. Okay, so now we can also ask that whether the certain symmetries that we know that electrodynamics should maintain, can it constrain the corresponding Lagrangian density? And if it constrains, then what is the Lagrangian constrained Lagrangian density, and then what are the equation of motion implied by that particular Lagrangian density? Okay, so that is going to be our way forward. That is going to be our approach. So we are trying to use certain principles or certain physical conditions to constrain the Lagrangian density. Okay, in general, we can write down any Lagrangian density involving the 4-vector potential, but we would like to constrain that using the fact that there is Lorentz covariance, etc., etc. Okay, there is Lorentz invariance, etc., etc. And we want to see that if, just based on symmetry grounds and with some physical assumptions, can we constrain the Lagrangian density so much that we have a unique Lagrangian density from which the equation of motion that follow for the gauge field are essentially these Maxwell's equations. Okay, so is that possible? Okay, so that is the kind of approach that we are taking. You see, this is the idea. This is the beauty of the thing. Now in this sense, we are in some sense using symmetry or physical expectations or physical conditions to derive the Maxwell's equation. Historically, it has proceeded in a way that we essentially did experiments and figured out, what the right theory was. Okay, so there were lots of experiments that were going on, and there were different theories, and Maxwell came and put them together. Once you put them together, then Einstein discovered relativity. And once Einstein discovered relativity, there was, and due to the contribution of many others, most prominently, Noether and, other very key ideas, it led us to the idea, to the notion that maybe the way to think about theories are essentially symmetries. So if we use the symmetries to constrain the Lagrangian, okay, once we can write down a Lagrangian which is constrained enough, then probably the dynamics of the corresponding degree of freedom is just predicted based on symmetry ground. Okay, I hope the philosophy is clear. So this is a bit of a philosophical point of what I'm trying to do here. Apart from the fact that, I'm going to write down the Lagrangian for electrodynamics. Okay, so you can ask, why am I caring about that? I have written down equation of motion. I have found solutions to it. I have done everything. You know everything about electrodynamics that goes on around you. But then, why do I care about writing down a Lagrangian? Okay, so the reason why I do that, or do care about writing that, is basically this philosophy. That, this idea in some sense gives us a derivation of Maxwell's equation based on symmetry grounds. Okay, so I hope this point is, I hope you can appreciate this point. Okay, it's a bit of a subtle point, but I hope you can appreciate this point. Okay, so of course, can we constrain it like, to a unique Lagrangian? And the answer to that is no. We can't in general do that. But let's see how much can we do. Okay, so of course we need Lorentz covariance. Okay, we need Lorentz covariance. And another thing that we have seen is when we give description in terms of the vector potential, then there is a redundancy of description. Okay, there's a redundancy of description, and we have to be careful that physical things that we write down is not redundant, that does not suffer from that redundancy of description. Okay, so we need to care and ensure that our Lagrangian is not only Lorentz invariant, okay, or the equation of motion is not only Lorentz covariant, okay, but it is also gauge invariant. So we want the equation of motions to be gauge invariant. Okay, as we know that Maxwell's equations are gauge invariant because it's expressed in terms of the electric and magnetic field, which are gauge invariant objects. But so because now we are caring, we are trying to think about ways in which we can constrain the Lagrangian density to begin with. Okay, so these are the two principles that we can use. One is Lorentz covariance or Lorentz invariance of the Lagrangian density, and the other is gauge invariance of the Lagrangian density. Okay, and again, this I'm not discussing, it's just beyond the scope of this course. This idea of gauge invariance is also can be thought of as a symmetry, although this is a redundancy of description, as I have been trying to advocate. But this can be thought of as a local internal symmetry, and again, that is what we are trying to implement here: a local internal symmetry. Okay, so this is in physics terms. Okay, so but essentially, what we want is we want to write down terms in the Lagrangian which are Lorentz invariant as well as gauge invariant. Okay, so for instance, if we have a term which is mu. Okay, of course, this is a term which is Lorentz invariant because the indices are contracted, but this term will not be gauge invariant. Okay, so therefore, we will not write down such terms which are although Lorentz invariant, but these are not gauge invariant. Okay, so as we know, the objects that we can construct out of these degrees of freedom, the vector degrees of freedom, the 4 vector degrees of freedom, these objects which are gauge invariant are essentially the field strength or the dual field strength. Okay, so this tells us we have to construct the Lagrangian in terms of the field strength or the dual field strength. Okay, if we want to write down a local theory. Okay, so basically that is the reason why we should think of the AMUs. That gives us a sufficient constraint. That already constrains the equation very much. Okay, so right. I want to mention one little thing here. So you might wonder, why am I considering this AMU as the fundamental degree of freedom rather than the electric and the magnetic fields themselves? Okay, so the reason for that, it's like, given the structure of the equations, the way I have discussed, it is already obvious that these are probably more fundamental than the electric and magnetic fields. But there is a second reason. Okay, in this particular theory, like of electrodynamics. Okay, I mean this is slightly advanced, but let me just mention it still. I mean there are observables, non-local observables in this theory, which are not electric field or magnetic field, okay, but there are some integrated version of the gauge field that are also gauge invariant. Okay, so these are called, if you like, Wilson lines in this. There are some observables which are like that, and particularly, they become very much important and relevant in the quantum version of the theory. Okay, but also, so therefore. In some sense, in order to also describe these observables, we need the gauge field rather than the electric and the magnetic field. So the electric and the magnetic field and just the Maxwell's equations, cannot give us the full description. We need the potentials. Okay, we need to go into the. So you might think that the potential is just a equation solving trick, but it's not that. Okay, there are observables which depend on the potential rather than the electric and the magnetic field. Okay. So if you have heard about Arno-Bohm effect, for instance, I'm talking about things like that. Okay, so there are observables where through which you can actually directly, get, directly it cares about there are observables which cares about the potential directly rather than the electric and magnetic field. So this was more of a throwaway remark, but essentially, we are on track. We want to consider these as the main degrees of freedom, mu as the main degree of freedom, and we want to proceed and we want to construct a Lagrangian density for mu, which is Lorentz invariant, gauge invariant, and also apart from this, we want to ensure that it is time reversal invariant. Okay, why is that so? Again, this is a symmetry principle. It's a discrete symmetry. The symmetry is t going to minus t. Okay, so if we just go back to our Maxwell's equation, then we will see that this is true for the Maxwell's dynamics. So did I write down the Maxwell's equation somewhere? Probably not yet. Or did I? Yeah, I think I did. Yeah, here. So you see here, if I make time going to minus time, okay, then this equation, let's say, does nothing. There's no time here in this equation. In this equation, there's a time derivative here. So this term flips its sign. Okay. But if I change t to minus t, then let's say, this current will also flip sign. Okay. So if I flip t to minus t, then something which was going in this direction will start going in the opposite direction, right? So that is the idea for which the current will flip a sign. And we'll see that this equation will remain invariant if b goes to minus b. Okay. And again, this equation will remain invariant if b goes to minus b. And for this equation, if b goes to minus b, then t goes to minus t, then this term is also invariant. Okay. So the whole set of Maxwell's equations, as written in this way, are invariant under t going to minus t. Okay. So for this reason, we would also incorporate that into our list of symmetries that we would like to implement for the Lagrangian density. Okay. Apart from these three symmetries, apart from these three symmetry principles, so again, let me mention that these three symmetry principles gives us a lot of constraints, but it doesn't constrain or doesn't restrict you from writing down terms which have higher and higher derivatives. So you can take terms, for instance, you can take something like f mu nu. This is a scalar clearly, okay, and then you can write down terms which has arbitrary powers of this, which has higher and higher derivatives. Okay, so this term would be consistent with all the symmetries, and there can be many powers of this term in the Lagrangian density, and those powers would have higher and higher number of derivatives on the scalar, higher and higher number of derivatives on the gauge field. Okay, so in general, it may not be on a single gauge field, but they will have higher and higher number of derivatives if we do the derivative counting. Okay, and for reasons that I mentioned during the scalar field discussion, those higher and higher derivatives can be neglected on the basis that we are interested in the physics of a length scale which are large compared to some small length scale. Let's say, we have experimentally probed up to some small length scale. Okay, it's a very tiny length scale, but there's a restriction, beyond which we cannot probe experimentally. Okay, this is a restriction of the apparatus, if you like. Okay, so if we are interested in the electromagnetism, okay, firstly, the classical field theory probably breaks down much before we reach that length scale. We have to do the quantum version. But again, just for this philosophical discussion, if we take this, okay, so once we are doing the Lagrangian formulation, there's a way to also make this and convert it into a quantum theory starting from this Lagrangian formulation, and that's why this question about higher derivative terms is also relevant for the quantum theory as well. Okay, so basically, the reason that we are ignoring such terms is the fact that if we are dealing with a theory where the fluctuations of interest are larger than a given length scale, then basically, the wavelengths are larger than a given length scale, which you can think at the moment as our experimental limit of looking at the smallest length scales. Okay, so there is an experimental limit to that, and that you can think of the fluctuations of interest that we are able to detect. Maybe those wavelengths are larger than that wavelength, larger than that length scale, and in this sense, in terms of this small parameter, okay, this dimensionless small parameter between the ratio of these two length scales, okay, these higher derivative terms are suppressed. Okay, and experimentally, we have also, we have not seen any signature of these higher derivative terms in whatever distance we have probed so far. Okay, so it is possible that because of some deeper reasons or because of no reason at all, these higher derivative terms are just not present. Okay, that is also possible. But if you are writing down some effective theory at some length scale, then typically these higher derivative terms are suppressed in terms of this, in terms of in the notion of a derivative expansion. Okay, so that's what as I said, there are various reasons, various ways to think about it, particularly when you do the quantum theory. But effectively, the reason is conceptually very similar to what I just said. Okay, so with that in mind, if we ignore the higher derivative terms, and if we just care about only terms involving two derivatives, okay, so apart from these three symmetries, we are ready to write down terms involving two derivatives only. Okay, and then let us see what are the various terms that we can write down in the Lagrangian density for this, just one degree of freedom, which is this vector field, vector potential, this mu. Okay, let's try to investigate that. So you will see that there are only two terms that you can write down. Okay, so as we have seen that f mu nu and f mu nu f tilde mu nu, these are of course these are gauge invariant because it's written in terms of f completely. But also we have seen this is Lorentz invariant because this is the indices are contracted, and we know that this term is proportional to e square minus b squared. Okay, probably you need a c square. Okay, and this term is proportional to E dot B. Okay, this we have seen before. Okay, of course you can also have a term which is f tilde mu nu, but this can be written down in terms of these two terms. Okay, it's not a linearly independent term, so you need not consider, writing that term would be effectively writing some combination of these two terms only. Okay, so it's not essential to be considered. Okay, so you might think that you might want to add a term like this, del mu nu del mu nu, but this object is clearly Lorentz invariant, but it is not gauge invariant. Okay, so I give you this as an exercise to show that a term like this is not gauge invariant. Okay, similarly, a term like this mu would not be gauge invariant, and therefore you cannot write it down in this list, because so of course apart from this thing, you could have asked whether can I write down some function of this term mu, right? This is something which we did for the scalar field. Okay, but that is not possible. That would be like a zero derivative term, so that would be definitely allowed if you are allowed to do that. But the gauge field, as you know, is not invariant under gauge transformation. Okay, or this potential field, or this 4-vector potential, is not invariant under gauge transformations, and therefore those kind of terms should not be allowed by gauge invariance. Okay, although they are Lorentz invariant, but it's not gauge invariant. Okay, so but you see, the problem is this term, as I said, is E dot B, right? This term is E dot B, and therefore if you do a time reversal symmetry, then this term is not invariant under time reversal symmetry, because B goes to minus B, so this term will go to minus itself under time reversal. Okay, so this is not invariant. On the other hand, this term being E square minus B square, okay, this is invariant even under time reversal. Okay, So because this is invariant under time reversal, okay, therefore this is the term that we can write down the Lagrangian in terms of this particular term. Okay. So essentially, this is just a comment. I mean, the time reversal, invariance, this term not being time reversal invariant can be traced back to the epsilon tensor, which is present in the definition of the dual field strength. Okay. So that is the reason why this thing is not invariant. So you don't have to look into this kind of transformation at all. I'm saying this because you're familiar with this. But if you just look at this expression and see how this contains the epsilon only once, and therefore because of the presence of the epsilon, this term will not be time reversal invariant. Okay, so in that sense, you can forget about this term. But if for some reason the time reversal invariance is not a good symmetry, then you have to start keeping terms like this. Okay, you have to remember that. Okay, so essentially, you see, these three conditions and the fact that we have to deal with two derivatives fixes the Lagrangian density to an object like this in terms of the field strength. Okay, so you should try to come up with examples which are consistent with this theory, these symmetries, which I may have missed. So please do come up with more examples and see and try to convince yourself whether this is uniquely fixed or not. Okay, whether you can write down more terms, you should try to experiment. Okay, so maybe you need some more assumptions. This is not enough. Okay, maybe you should put in some more physical inputs into the construction of the theory. But it seems to me that if you give these three conditions plus the fact that plus the fact that you have two derivative theory. Okay, of course there can be higher derivative. You can just write down the square of this term also. Okay, that would also be a totally valid term, but that would have four derivatives. So if you restrict yourself to two derivatives only, then this is the unique term that you can write down. Okay, so now if this is the unique term, then let's start with this Lagrangian density and try to perform a variation of the action for thinking of this as a functional of the gauge field or the potential, for potential. Okay, I keep referring to this as the gauge field because of some reasons, but this is what I mean. When I say a gauge field, I mean it's the four vector potential. Okay, so you should take the action and vary it with respect to the four vector potential. And if we do that, then you see what happens. So the variation. Okay, firstly, okay. So we can take. We should, for extremizing the action, we should set the variation to 0. Okay, and when we take the variation, okay. And this sign is more of a convention. Okay, it's more of a convention, which we, usually keep. It's the convention for which you essentially write your Lagrangian for the harmonic oscillator as kinetic energy minus potential energy, and not minus kinetic energy plus potential energy. Okay, it's that kind of convention that we are following here. Okay, so if even if you did that, if you put in a minus sign in your action, your equation of motion would be invariant, right? You get the same equation of motion. But there's a convention we follow that we write it as kinetic energy minus potential energy. Okay, and that is the same convention which leads to this kind of a minus sign here. And once we have this Lagrangian density, we write down this variation in this form, where the variation can hit either this half or this one. So that takes away a factor of 2. Okay, so that's like two terms, which is the same term. So that 1/4 becomes half here, and now this variation acts on this thing. Now this so the variation acts on this f, but the f has two terms. There's a del mu nu and there's a del nu mu. Okay, with a minus sign. but these terms are contracted with this antisymmetric term here. So this term here, if we write it out, is identical to this term if we just exchange the mu and nu. Okay, so it's identical, so that also takes care of another factor of 2 here, okay, which essentially, so there is this 1/4 factor which is completely cancelled, because one is because the variation can hit either this one or this one, that gives me a factor of 2. And the other thing is when we write this f mu nu in terms of del mu nu, okay, that takes care of a factor of 2 here. Okay, so this is what we have, and the variation goes inside the derivative now. And then as you know, the standard technology is to take the derivative and put it here at the expense of a sign, and then that you do by writing down this total derivative. Okay, so when the derivative hits this f here, then you get this term which cancels, and when the derivative hits this one here, then you get this term back. Okay, so this is just an identity here. Okay, and this term is a total derivative, and again, if we say that the variations, you know, vanish at the endpoint of space-time, then you can forget about this term, and you are left with this one. And if this has to be equal to 0 for an arbitrary variation of the gauge field nu, then we must have the equation of motion, which is del mu f mu nu equal to 0. Okay, the divergence of the f field strength is equal to 0, and this is precisely the source-free Maxwell's equation. Okay, so this is how, in some sense, symmetries and the criterion that we want two-derivative theory, they constrain our equation or the dynamics of the gauge field to an extent which is this thing. Okay, so again, so I have tried to give you motivation why this is the mu is the right degree of freedom for this problem. I mean, if you want to give a relativistically covariant description of electrodynamics, then you have to talk about this 4-vector potential as the degree of freedom. Okay, so this tied very intimately this fact that mu is the degree of freedom, right? Degree of freedom to think about is tied intimately with the fact that you are talking. You wish to give a manifestly relativistically covariant description of electrodynamics. Okay, so very good. So with that, we have derived the Maxwell's equations in some sense. Okay, starting from some philosophical inputs, we have derived using this variational principle or this extremization of action principle. We have derived the Maxwell's equation in this way. Okay, so what about the source? You know, this is the source-free one. What about the source? So as you know, the source would appear here as mu naught times J nu. Okay, so if there has to be a term like this, you can just by inspection write down a term like this. If you take the variation, this term is going to give you the usual Maxwell's equation. Okay, and of course there will be a total derivative which you can forget. So this term, when you vary, it will give you the usual, you know, the left-hand side of the Maxwell's equation. And here, because there is one single mu here, okay, that will become the variation. As you do a variation, it comes and hits this mu here. Okay, that's the only degree of freedom. That's the function with respect to which there's a set of functions. You know, there are 4 functions. You know, with respect to which you are trying to extremize this s. Okay, as a functional variation. Okay, so therefore this delta will hit only this mu, and if the delta hits mu, then you get a mu naught times J mu, which remains here, and if it remains here, right. So if it remains here, then you get the Maxwell's equation with the sources now. Okay, so the sources, this current J nu, you know, you can just multiply it with mu contracted. Of course, this is Lorentz covariant, and you can write down a term like this. Now you must be wondering that what am I doing here? Because I have written down a mu in the Lagrangian density, and just now I was trying to advocate that you cannot write down terms like mu nakedly, you know, without any derivative and making it the field strength, because then there will be a problem with gauge invariance, right? Because obviously the mu under a gauge transformation becomes mu minus del mu chi. Okay, and then this term will not be invariant because there will be an additional term which is J mu contracted with del mu chi. Okay, it's definitely not going to be invariant under that. So what is going on? What is going on here why have I, but it gives the right equations, right? It gives the right equation. So there must be something going on. What is going on? Let's see what is going on. So if I take this Lagrangian and do a transformation, so this transformation I have said I've made a gauge transformation. So this is the question, that is this Lagrangian density, okay, is this additional term, is this gauge invariant or not? Okay, so in order to do that, let's do a gauge transformation, and as I said, the A mu develops this del mu chi term, which is this additional term under a gauge transformation, and I have denoted it by a chi here. Okay, the action now also depends on chi because you have done a gauge transformation and it doesn't seem to be invariant under it. Okay, so the variation in the action under this gauge transformation, which is chi, denoted by chi, this variation is not the functional variation. Okay, it's just the fact I have taken S chi minus S, where I have taken this Lagrangian density, where I have done the gauge transformation and subtracted out the Lagrangian density without the gauge transformation. This one I have just subtracted out from here and written this expression. So this is the additional term for which this variation is not zero, and this is the additional term for which the action is not gauge invariant. Okay, now let's look at this term. This term is, this some constant which can be pulled out, and del mu of chi times j mu. Sorry, I have messed up very badly here. Where did I start messing up? Okay, so I have started messing up from here. So this one I should write j mu, and here, this has to be a scalar, so this is a j mu. Okay, and so now this term is going to be j mu, right? Okay, so very good. Now if we take this term here that we have found as the change in the action after the gauge transformation, if we look at this change is not zero because of this term. Now because you look at this term, and then you can say that you can do write this term again as a total derivative minus the derivative acts on j mu. Aha, this is complete mess. I'm so sorry. Right. Okay, so this tells us that we can take this term and do a total derivative. This is a total derivative minus this piece. Okay, so again, this total derivative becomes a boundary term. Okay, this total derivative becomes a boundary term, and if we have localized current densities, and if we set initial conditions for this chi, so that the boundary of space-time, this term vanishes, then we don't have to care about total derivatives. Okay, we are anyway not worrying about boundary terms, so we will select the boundary conditions such that we don't have to care about them. Okay, so very good. So now we focus on this one. This is the only non-zero term which is there. But as we see, if this if the action has to be gauge invariant, then this has to be zero. Okay, and if this has to be zero, then for an arbitrary scalar field chi, then it implies that the divergence of the 4 current density, that must vanish. Okay, so you know what this equation is, right? This equation is basically the charge conservation equation. Okay, and this j mu is a conserved current, by that terminology. Okay, so therefore this what we find here is that if this j mu, is a conserved current, that means del mu j mu is equal to 0. If this is a conserved current, then this term that we have written down is gauge invariant, again up to boundary terms. Okay, like the boundary, we have to be careful to set boundary conditions up to total derivatives. Then this object is gauge invariant if the divergence, the 4 divergence of this j mu vanishes. Or in other words, you can say that the gauge invariance of this term implies that this current must be conserved, or the divergence of this current must be equal to 0. Okay, So in this sense, the conservation of charge is a consequence of gauge symmetry, if you like. Okay, in this sense, the conservation of charge is a consequence of the gauge symmetry. Okay, so of course, if you look at the equation of motion, if you look at this equation of motion that we have here, and if you take if you take a del nu on this equation of motion, okay, then this term obviously vanishes because mu nu, symmetric, antisymmetric, and it just follows that del mu, it follows from the consistency of the equation. But if you look at it or think deeply about it, the reason why this del mu j mu is conserved is essentially can be traced back to the fact that the Lagrangian must be gauge invariant. Okay, it can be traced back to the fact that the Lagrangian is gauge invariant. Okay, so this also ties up with a theorem which is due to Noether. It's called Noether's theorem, that if you have a continuous symmetry, in this case, this quote-unquote gauge symmetry or gauge redundancy, which is like a symmetry because we are trying to implement it as a symmetry. We want to implement gauge invariance in the Lagrangian density. Okay, so if we have this kind of symmetry, then there has to be. I mean, I'm saying things which are like even a little bit inaccurate, but this can be made much more precise. In what I'm saying, they can be made much more precise. But you want to if you like, then that symmetry, if you like, gives us the conservation of the charge. Okay, it gives us the conservation of charge. Very good. Okay, so we have now seen the Lagrangian from which the Maxwell's equations come from. Okay, so now it is time to do a little bit of some general discussion. So now, so far I have been doing the variation directly and I didn't write down Euler-Lagrange equation for you, but let me write it down for you for a general, for a general field. Okay, so let us say that we have some degrees of freedom which is denoted by this xi. Okay, so this xi can be a phi, it can be a mu, it can be some object, it can be some tensor v mu nu, okay, whatever you want. Okay, so if you have such objects, then you can consider xi to be denoting the various components of mu. Okay, so let's say you have mu, so it has like 4 components, then you have like 4 xi's like this. Okay, so this is a collective representation of all the field degrees of freedom that you have to deal with. Okay, so as you have seen, given the degree of freedom and some symmetry conditions, and again some restriction on the number of derivatives, we have been more or less able to fix the action. Okay, or the Lagrangian density. Okay, so even if we are not able to fix it, we can try writing down several theories and try to go back and check with experiments whether that is the right theory. Okay, for Maxwell's electrodynamics, that works. Up to the length scales that we have tested, it is a beautiful theory. Okay, at some point we have to do the quantum version of the theory, but it's a very, very good theory. Okay, but now here in general, let's say you are doing talking about a field theory where all the field degrees of freedom are denoted by xi. Okay, then you write down a Lagrangian density where you have xi as well as some derivatives acting on xi. This is the form of the Lagrangian density. Okay, so it can depend on the fields themselves. Okay, like we have seen for the scalar field, you could have written down a function v of phi. So there can be a xi dependence directly, and there can be derivative of xi that is there. Also, it is possible. So here, in doing this exercise, I am thinking of xi as a collective degree of freedom, which refers to all the fields. Okay, very good. So if we do that, then we'll notice, let's do the variation and try to find out the equation of motion in terms of the Lagrangian density itself. Okay, that will give us this Euler-Lagrange formula, that given any Lagrangian density, can we write down a formula which is the equation of motion. Okay, that's what I'm trying to do. Okay, so and therefore I'm keeping this discussion general. This xi can be a vector, scalar, or anything you want, any degree of freedom that you want. Okay, in general. So if I now try to perform the variation with respect to xi and extremize s, okay, I'll set 0 as the variation, this thing. And now, as you can see, L can be a function of xi. Okay, so the variation can hit the xi's here. So therefore, I take the derivative of L with respect to xi and the variation of xi. Okay, it's just, the way you perform differentiation. Okay, think of this as a function of xi and the derivatives of xi. Okay, and then you can take the variation with, the differentiation of the Lagrangian density with respect to the derivative of xi, and then you have a variation of the derivatives of xi. Okay, so now once you have these things, then this term, is a term for which, as you can see, the derivative acts on the variation of xi. So we have to perform the same game. We have to take the derivative out, okay, so that this becomes a total derivative term, and then you are left with, again, this term remains, and then there is a derivative which is acting on here with a minus sign, okay, because this will cancel the additional term that comes from here. Okay, so that comes from here. Okay, so now this is a total derivative again. This gives a boundary term, and if the variations vanish at the boundary, you can set it to 0, and it's the usual story. So now you can group this bracketed term and multiply it by this variation. This is the thing that must be set to 0 if the action has to be extremized, and this therefore is the Lagrangian, the Euler-Lagrange equation. Okay. So given the Lagrangian density now, this is the Euler-Lagrange equation. As you can see, this term is the term where you differentiate the Lagrangian density with respect to fields directly, and this is the term which you differentiate with respect to the derivative of the fields, and then you basically take a further derivative on top of that. Okay, this is the Euler-Lagrange formula for fields. Now let's immediately test it for our electromagnetism. Okay. Again, there was a sign here. Our sign convention was that, there was a sign here, minus 1/4. And now if I write this using the antisymmetry of F mu nu, I could write using the antisymmetry of F mu nu, I could write this as del mu mu, okay, without any problem. And then, that would just give me a factor of 2, which will cancel 2 in the 4, okay, in this 4 here. Okay, so here you see, again, I don't know I hope you are able to follow this. You see this F mu nu, I can write one of these F mu nus, I can write as, let's say, this one of these F mu nus, I can write as del mu, so, yeah. Let's say this one, I can write as del mu a nu minus del nu a mu. Okay, so there will be two terms which are multiplying this F mu nu here, and these two terms are equivalent. That gives me a factor of 2. Okay, that's why. Okay, so now if I have this, then I can now I want to use this Euler-Lagrange equation. Okay, so I need to know what this term is first. Okay, so of course this doesn't have mu, the field. All the terms have the derivative of the fields. That's all that is there. Okay, that's all that is there, and then you can perform a derivative. So this is equal to 0 because there's no clear dependence on mu here. Okay, and so now you can perform a derivative with respect to the del mu a nu. For every component nu, you can perform a derivative. So this equation now xi, you should think of as every component. For every component of mu, there is an equation, corresponding equation which is given by this xi. Okay, so therefore, so for a0, you will do a similar. You will write a similar equation, and so on. Okay, this can be represented together by considering a new index here. And if you perform a variation of L with respect to, if you differentiate L with respect to del mu a nu, which is this kind of term here, then this differentiation, there's a term like this here as well as here, so that gives me a factor of 2, and essentially, this thing gives me minus, this minus sign remains, it gives me minus F mu nu. Okay, so that is how, I'm just trying to demonstrate how to use the Euler-Lagrange formula. Okay, where you have, I've written only a xi here, but if you have a vector field, then for every component of the vector field, you should think of as one of the xi's, and there'll be an equation for every degree of freedom. Okay, that's what I mean. Okay, now if you take this and plug it back into a Lagrange equation, if you take this f, and plug it back in here, this is equal to 0. So you will have del mu f mu equal to 0, which is the your original Maxwell's equation without sources. Okay, so very good. Yeah, before I have some exercises for you, but before I do that, let me point out one fact. So we perhaps you can wonder that if we have this Lagrangian density, okay, if we have this Lagrangian density, you might want to write down a term which is like, the one that we did for the scalar field, some m tilde mu mu. Sorry, mu mu. Okay, you might want to write down a term like this. Okay, so if you were to write down a term like this, okay, then this would be interpreted. This term would be interpreted as the mass of the scalar field. This would be interpreted as the mass of the gauge field, or if you like, the excitations of the gauge field. Okay, as I was trying to say, the corresponding quantum theory, the photon would have a mass. Okay, that those particle-like excitations would have a mass in the quantum theory, but in the classical theory also, the dispersion relation in an electromagnetic wave would be shifted by this mass. Okay, you can just work it out, the corresponding equation of motion. You will see that the dispersion relationship, acquires this term here. This term goes and sits in the dispersion relation, and that can be interpreted as a mass if you compare that dispersion relation with a particle. Okay, so I must emphasize that classically, that omega and that k or momentum, they have nothing to do with any particle. Okay, or they are not even interpreted as energy, etc. Okay, in general. Okay, but the energy is basically E square plus B square, etc., etc. We've done all that. Okay, but in the quantum case, that when multiplied by h cross, gets the interpretation of the energy of a particle of light, which is the photon. Okay, so those are all the things that are beyond this course, and we don't want to get into it. But I just want to point out this fact that a term like this, as I was emphasizing, is not possible. Okay, because of gauge invariance. Okay. So physically what you would say is the mass of the photon, or this is the popular way to say it, the mass of the photon is not allowed because of gauge invariance. Okay, this statement you might hear in different places, that the mass of the photon is not allowed because of gauge invariance. Okay. But I must say that this is for electrodynamics. This is right. But there's a way to give a mass to. There are mechanisms to give mass to gauge fields. Okay. In fact, we know cousins of electrodynamics. The weak interaction, which is a cousin of electrodynamics essentially, where the corresponding gauge bosons are massive. Okay. And that phenomena is called, or that mechanism is called Higgs mechanism. And, there are ways or mechanisms, or even for the scalar, this one, you can introduce, some kind of coupling with some scalar field and introduce a mass term for or you introduce a gauge, you can introduce a gauge invariant mass term for this object. Okay, the Higgs mechanism is a mechanism which ensures gauge invariance and as well as gives mass to the scalar field. Okay, so this point, you might want to keep in mind that a priori, if we are just writing down a theory just with the vector potential, then it is not possible to write down a term like this, and therefore there is no mass for the scalar field. But there can be a case of spontaneous breaking of the symmetry in the Higgs phase, or there can be Higgs mechanism, etc. Okay, there can be ways to give mass in a way, generate this term dynamically. So in those cases, you generate a term like this dynamically, where through some mechanism or through some coupling with other degrees of freedom. Okay, so that's the bottom line. Okay, I just wanted to mention this. You might want to keep this in mind. Okay, so now, very good. So I want to give you these two exercises. I'll again put it up in your assignment, but here I will just mention it. And so the first one is if we give up the idea that there's a time reversal symmetry, then we are allowed to write down a term like this. Okay, F tilde, this is the E dot B term, right? This is the E dot B term, and we can write down a term like this in the Lagrangian density. Okay, so I would like you to start from here and work out the equations of motion. Okay, what is the equation of motion and how it gets modified if we have this kind of a theta term. Okay, and I want you to study whether or not it is time reversal invariant. First, write the equation of motion in terms of electric and magnetic field, and then study its time, symmetry with respect to time. Whether you can make it time reversal invariant or not. Okay, so this I want you to study. Okay, and then the next thing is basically I want you to also look at the following. This part is basically gives these two terms would give rise to the usual Maxwell theory. Okay, now if you have a correction to that, which is a higher derivative correction. Okay, you see, apart from the fact that this is not two derivatives but four derivatives, four derivatives, right? This is a four derivative term. Just apart from that fact, it is gauge invariant, it is Lorentz invariant, and it is also time reversal symmetric. Okay, so you can see that if this is time reversal symmetric or not by writing it out in components. Okay, so this term in general would be allowed if you don't restrict yourself to two derivative theories. There are more other terms like this that will be allowed also, but I want you to pick up an example of a term like this, higher derivative term, and I want you to work out the Maxwell's equation from there, and in particular see how this term affects the Gauss law. Okay, that's the equation that I want you to focus on and study. Okay, and once you see what is the modification of Gauss law, then I would like you to come up with an experimental way to determine this value of this A. Okay, can you determine this value of this A given how this term modifies the Gauss law? Okay, this is an interesting exercise that you can do. You can suggest some experiment which you can do to constrain a term like this. Okay, so this I am leaving for an exercise for you guys to do. Okay, very good. So these are the two exercise problems that I want you to do. Okay, now the next topic, which I was so far silent about, is what is the Lagrangian for the Lorentz force. So we have spoken about the Maxwell's equation, but what about the Lorentz force? Okay, that is also something a part of our fundamental equations, and we can ask, can we derive it starting from some action or some Lagrangian and performing a extremization of an action or some action principle leading to the Lorentz force. Okay, can we do that? So that also can be done, and I have demonstrated it here for you. So essentially, let's consider a charged particle. Okay, a single charged particle, and if it is a free particle without charge, okay, then the Lagrangian for that is given by this expression here. This we have seen in previous video. Okay, and so this is basically the fork, the velocity of the particle. Okay, this is proper time d tau. Okay, so the free action is written like this, and the equation of motion which follows from here is basically this mass. This is interpreted as the rest mass of the particle, m times the forward acceleration. Okay, this comes out to be the equation of motion, m times the forward acceleration equal to 0. That's the equation of motion. Okay, for this action. Okay, so now we can ask that how can we modify this action so that this mass times x, this, we get the Lorentz force term here as well. Okay, how can we modify it, or can we modify it? Okay, so and from there, for doing that, we consider the fact that we know how to couple a current. Let's say now you have a charged particle. Okay, so if it is moving, then you have a current, and we know how to couple a current with a gauge field, which gives the right Maxwell's equation. Okay, that kind of coupling, as you remember, was something like J mu A mu. Okay, and that was basically a Lagrangian density. Okay, now we are trying to write down a Lagrangian for the particle. Okay, because it's a single particle, we are trying to write down a Lagrangian and not a Lagrangian density. So if you take the J mu and if you write it in terms of a current, now do the spatial integration. Okay, then you see this Q times U mu is the current, corresponding current. This we have discussed. It's a covariant current. Before also we have tried to consider. If you remember the Lorentz force, then the Lorentz force, while discussing the Lorentz force, we said that this was the form of the Lorentz force. Okay, as a 4 vector, this was the form of the Lorentz force, and there we interpreted this Q times U as the current corresponding to the point charge. Okay, moving point charge. Okay, so now if we do that, then basically we can write down this term, this interaction term. So the point particle being charged interacts with the gauge field, and this is the kind of term that follows from this current term, this mu, this term. This is the kind of term that follows. Okay, I must say that the current, depending on the matter content, what kind of matter you have, that can have different forms. Okay, that's why I have written it like that in the Lagrangian. Okay, so I am assuming that the current is gauge invariant current. Okay, it's because that went in. When I did the gauge transformation, I said it was not affect. The gauge transformation didn't affect the current. So I'm assuming that the gauge current is gauge invariant, and apart from that, I cannot say any more specific thing about the current because I don't know what kind of matter is participating in making this current, or what kind of matter is charged. Okay, so here I'm just doing particle dynamics of a charged particle, which is essentially talking to the gauge field through this term in the Lagrangian. Okay, so this is our starting point, and the current can be depending on the matter which is charged, it can be many things. I mean, it can be different things. Okay, so in fact, some of these matter fields are things that are charged under this electrodynamics. They also can be fields. Okay, instead of particles, they can be fields, and not only they can be fields, they can be they interact non-trivially only if they are charged fields. Okay, and if they are charged fields, then they also transform non-trivially under gauge transformation. Okay, but the current that you are you can construct out of it, that current is gauge invariant. Okay, you can show that. Okay, so basically right. I mean, so basically. Right. Basically, you can construct such things depending on the particular kind of charged object that you have. Here we are just considering particle dynamics of a single charged particle. Okay. So therefore, we are talking about Lagrangians instead of Lagrangian densities because we are talking about a particle. Okay. So now this is the free particle. So if you like, this is the part which is equivalent to the kinetic energy of the particle. And if you like, this is the part where the particle is experiencing, some kind of an interaction with the electric and magnetic field that should be captured in this way through this term. The main thing that I want to understand and appreciate is we are, in order to do this covariantly, or Lorentz in a manifestly Lorentz covariant way, we should think of these particle coordinates x mu. As a function of its proper time. So the particle is moving in some way, and tau parametrizes this world line of the particle. Okay, so the particle is moving in some way, and tau parametrizes the one line of the particle. Okay, and there are various coordinates. These coordinates, take various values on this on this wall line of the particle. Okay, and therefore these coordinates, if you specify them as a function of the tau, then I will know what the wall line of the particle is. Okay, by wall line I mean, you know, how the particle travels in space time. Okay, so therefore, so this is the function that I need to determine in order to know the dynamics of the particle. I need to express all my coordinates, all my space-time coordinates in terms of this intrinsic parameter that parameterizes this particle motion, which is the internal clock of the particle. You know, it's the proper time of the particle. Okay, in that sense. Very good. Now this, with this, I can, you know, this was the free part, and this is the part where the particle interacts with the gauge field. Now the gauge field, you see, so you know the idea is that you know there's a region where the gauge field is non-zero. Okay, and the particle is like, you know, moving in this region, and it interacts with the gauge field, you know, at the point, you know, let's say this is some point x mu of tau. Okay, for some particular value of tau. Okay, so the value of the gauge field here would be interacting with the particle. This is the local interaction that I have been, you know, mentioning. Okay, it doesn't, you know, the particle, you know, dynamics at this point doesn't care about what the gauge field is doing at this point. Okay, it just cares what the gauge field is doing at the location of the particle, and that's why this is the same degree of freedom, you know, same function that also enters into the argument of the gauge field. Okay, so that's the same degree of freedom. This is very important. And now we can take this action and this functional and try to extremize this as a function of x mu of tau. Okay, so if you try to extremize this, we do the variation and set it to 0. You know, that's the standard procedure. And you are already familiar with the variation of this part. You know, this you have already seen, you know, how to do the variation of this part. Okay, now for the variation of this object here, then you see there will be one term where the variation hits this. So it's the tau derivative of the variation of x, and then there is one term where there's a, you know, this one you know, is left, and this you know, the variation hits the a mu and the x mu's inside the a mu's, and then you just do, you know, because it's the function of this thing, so you'll do a functional derivative. So you'll do a first derivative of x mu, you know, this thing times the variation. This is how you just differentiate it, right? Okay. So there's a, you know, this object is nothing but del mu a mu. Okay, this object is nothing but that. Okay, very good. But now here there's a tau derivative, and there's a variation inside. So you have to play that same game. You have to write down a total derivative. So if you know, you take the tau derivative and put it outside. Okay, so you have to write down a term like right. So let's see. So right. So yeah, I have not written the total derivative term, but you know what I mean. So I have, you know, I can take this and write this as a dd tau of a nu times delta x nu. Okay, and here if I do that, then I will have one term when the derivative hits this guy, I will get this term back. But when the derivative hits this guy, that I have to subtract, and that I have subtracted here. Okay, so I've dropped this total derivative term from the fact that the variation vanishes at the endpoints. From that fact, I have ignored this term. Okay, and the rest of the terms I have kept. You see, this term is, you know, gives rise to this usual piece, which is basically m times, you know, if you can identify this m times nu, you know, this x4 acceleration here already emerged. And again, you know, here I have used the fact that u mu, you know, this is the same derivation, u mu is c squared. Okay, that I have used here, and that cancels this factor of c. And now here, right, and this term I have kept as it is. Okay, as it is there. Now, when there's a tau derivative on nu, I know that my nu's are functions of like x mu's, which is a function of tau, right? These are functions of this coordinates, which are themselves function of tau. So if you have to perform this differentiation, then you better, you know, first differentiate with respect to x mu, and then differentiate x mu with respect to tau. This is chain rule. Okay, so if you do that, then you generate a term like this, and this becomes del x mu del tau. And now you see the fun. You can take del x mu del tau common from these terms outside, and what you're left with here is precisely the combination which gives you the field strength. Okay, so you see it's magic. And therefore, then if you pull the delta x mu variation outside, this is the function with respect to which you are extremizing, then this is the 4 acceleration that you had before, and this is the Lorentz force. We have demonstrated this in the previous video, that this is the Lorentz force. It precisely comes out to be, so this part, if you remember, comes out to be gamma times q times E plus V cross B. That's what it comes out to be. And on this side also, a mu, this is like, gamma times ddt of m gamma V. Okay, this is that. And this factor of gamma cancels with this factor of gamma. It's just trying to remind you that this is what had happened. So please consult the previous video, what happened to, how, this is precisely the Lorentz force equation, how that comes about. So for this, you please consult the previous video. Okay, so very good. So this is my Lorentz force condition, and I also get the modification of the Newton's law out of it, immediately by a variation principle. Okay, starting from a Lagrangian density. Okay, so this is something which is nice, and we just demonstrated it. Okay, as an exercise for this part of the discussion, you might want to do the following. You might want to so you remember, for the free particle, there was a time when we considered, this d tau we wrote as, dt times, this factor gamma. Okay, this is gamma. So this is like, I'm trying to write proper time as, so d tau I can write as 1 minus v square by c square to the power half times dt. Okay, this is what we can do. And so this dt is dx dt now. This is like a 3 vector now. Okay, this is just a 3 vector square. How did I miss the square? Okay, this is v square by c square. Okay, and so we have, if you remember our discussion for the free particle, then we have started from here, and then we calculated the the conjugate momentum conjugate to this x, and the Hamiltonian, corresponding to this Lagrangian, okay, of the free particle, and we had some nice observations about the momentum and the Hamiltonian. Okay, so but now there's this term which is there. Okay, and this term is there, and so you can think of this as x of t and t, this thing, and also you can this u mu, if you remember, is nothing but gamma, c, and v. Okay, so these are the various components, and remember, a mu component is basically phi by c and a vector. Okay, that is minus a vector for the one that is below. Anyway, so you can write this out in terms of the various potentials. So this is the action for a particle where you are essentially rewriting it. This is not manifestly relativistically covariant, okay, but x of t essentially is the degree of freedom for the trajectory, right? So that you might want to think of it in that way as well, okay, if it is not manifestly relativistically covariant. So that would give you the corresponding momentum and the corresponding Hamiltonian. I leave this as an optional exercise for you because this is more of a sidetrack. If you've learned your Hamiltonian and your conversion of Lagrangian to Hamiltonian, etc. very well, then this should take you just 2 minutes, and it's going to give you some very interesting results, which is super useful later on. Okay, how to couple a particle with a gauge field, that thing. If you do the quantum version, if you take a like you can take that object, and if you place a particle in some magnetic field, then you get this physics of the Landau levels, etc. That comes out of this consideration. Okay, so again, that kind of like there are some quantum considerations, etc., etc. But Essentially, this will be a super useful classical exercise to do to consider the corresponding Hamiltonian and the momentum. Okay, very good. So now, for the last topic for this video, this is the Noether's theorem. Okay, we want to discuss the Noether's theorem a little bit. I want to give you a little bit of a whatever we can do with our present knowledge. Of course, there are things that we this is beyond the scope of this course, but I'll try to give you a little bit of an idea about what goes on. So Noether's theorem tells us that for every continuous symmetry, there's a conserved current. Okay, and this is very important, continuous. Okay, remember the discrete symmetry, which was time reversal? Okay, that is discrete because there is no continuous parameter associated with it. Okay, it's just t going to minus t. Okay, that's a discrete symmetry. And but if you have a continuous symmetry, so that symmetry, t going to minus t will not have a conserved current. Okay, but the Lorentz symmetry or the gauge symmetry, as we already saw, the gauge symmetry had a conserved current, corresponding, charge conservation statement. So similarly, you can ask that, the other symmetries of the problem, what they lead to, or what kind of conclusions or current conservation they lead to. Okay, so in general, the current conservation has this following form: is the divergence of some quantity. It can be a 4-vector or a tensor. So it's in general the divergence of a tensor that's equal to 0. This is the statement. This is what I mean when I say a conserved current. Okay, there exists a quantity, a tensor quantity, whose divergence is 0, and as soon as its divergence is 0, then this J naught, this quantity can be interpreted as something analogous to the charge density, whose integration over space is conserved. Okay, that's why it's a conserved current. Okay, so I hope you understand that. So basically our target actually, okay, although I will do a general discussion of the Noether's theorem, but my ultimate goal is to understand what is the consequence of translational invariance or translational space-time translational symmetry. Okay, what is the implication of that for this theory? And as you will see, this leads to the conservation of energy and momentum for electromagnetism. Okay, because this is a field theory, we have to develop slightly advanced techniques to understand in covariant manner. So we already have seen energy and momentum conservation starting from the equation of motion, right? That was the Poynting theorem and the conservation of the momentum theorem. Okay, if you consult the previous videos. Okay, but now we want to do it covariantly, and we want to understand how all that fits together, and that, if you want to do covariantly, follows from the Lagrangian by a procedure due to Noether, and that Noether procedure is basically tells us if there is a continuous symmetry, then we should be able to write down a corresponding conserved current. Okay, and energy and momentum conservation is just a conserved current corresponding to space-time translational symmetry. Very good. So so that's what we want to do, use Noether's procedure. So for doing that, we start with our again, we go on to this general description. Okay, again, xi is some field. Okay, it can be components of some vector fields, or it can be a scalar field, or it can be a collection of scalar fields. Okay, it collectively represents all the field degrees of freedom. Okay, and this is the action which we can extremize and write down the Euler-Lagrange's equation, for instance. Okay, now let's say the theory has a continuous symmetry. This thing continuous is very important, because if it has a continuous symmetry, then we can write down this particular transformation. Okay, the field becomes the field plus epsilon times some variation of the field. Okay, this is this is not functional variation that I'm doing, although I'm using the same notation. But this is the variation of xi because of some symmetry operation. Okay, I will demonstrate it very soon with translational symmetry. You'll see what it means. But you should try to this is not a variation, but this is a symmetry operation. Okay, for instance, let me just say it here. So let's say if let me just say it here. I will get back to it later also. So for instance, if there was x mu, you did translations x mu a mu, and there was a xi. Okay, this you could write, and let's say mu was infinitesimal. This epsilon is an infinitesimal parameter here, okay, corresponding to a symmetry. So, and here there are like 4 infinitesimal parameters corresponding to mu. Let's say this is a infinitesimal translation. Then this you can write, if this a is small, this you can write as xi of x mu plus a mu del mu of xi, right? If the a is small, you can forget about higher order terms. And in this particular case, okay, example, okay, this is, sorry. Okay, this is an example. And in this particular case, this thing that I've written here, delta xi, is nothing but del mu of xi. Okay, corresponding to all the parameters. You know, this is epsilon is like, you know, there are 4 such epsilon parameters, which is mu, and the corresponding variations are, you know, del mu of xi. Okay, so this is what I mean. You know, I can write down an expression for this concretely. Okay, if I know what the symmetry is, I can write down an expression for this concretely, but here I'm trying to do an abstract description. So I'm just assuming that this is the variation. This is the change in the field due to the symmetry transformation. Okay, this is a change in the field due to the symmetry transformation. Very good. Right, now with this, what we can do is we can ask, what is the change if it is, you see, if it is a symmetry, then the Lagrangian must be invariant. Okay, if it is a symmetry, then the Lagrangian must be invariant. So we can try to perform the symmetry transformation on the Lagrangian. Okay, and what is actually true is it may not be actually invariant, but it can give rise to a term which is a total derivative. And as you know, total derivative would give rise to boundary terms, and it will not affect the equation of motion in any way. Okay, so the equation of motion will be invariant if the symmetry transformation gives rise to some total derivative terms in the Lagrangian. Okay, so this is the way in which the Lagrangian can transform under the symmetry transformation if there is a symmetry in the picture. Okay, it can transform at the leading order for infinitesimal transformation. You see, you know, this is the point where the assumption that we have a continuous symmetry comes in. Otherwise, we will not have an infinitesimal parameter characterizing infinitesimal version of the symmetry transformation. Okay, this is the reason why you need a continuous symmetry for this argument to work. Very good. So the Lagrangian would transform as del mu of some object. Okay, this object, whatever I have written here, you know, I have invented the symbol, or you know, you can call it I, J, or whatever, I, maybe, your script I. Okay, this object is basically, you will say that the Lagrangian must transform as a total derivative of something so that the equation of motion are not affected. And because, you know, it has to be proportional to the parameter of the transformation, which is a small parameter here. So it has to be proportional to epsilon. That means the change in Lagrangian because of this symmetry must be proportional to del mu of J mu. Okay, that's the change in L. Okay. Now, you know, this is, you know, something that can be stated in general about the Lagrangian, you know, how it transforms. Now, we can also check whether, you know, the Lagrangian depends on the fields and the derivatives. Because it depends on the fields and the derivatives, and the fields and the derivatives themselves transform under the symmetry transformation. So we can try to implement it at that level. Okay, we can try to say what this delta L is, where I am trying to implement the change at the level of the fields. Okay, so let's say the L depends on xi, so there will be del L del xi, and epsilon delta xi. You know, this delta xi is the way in which the field has transformed, remember. Okay, so therefore, you know, this is just again, you know, trying to find out, this is a continuous parameter, so I can do this kind of variation, you know, of the field. But now it is a symmetry transformation. I'm not doing a, you know, functional variation for minimization of the action. You know, that's not what I'm doing. I mean, this object is a known object. You know, as I demonstrated for translation, this is a known object. Okay. How the field transforms, we should know if there's a symmetry. Okay. So therefore, and then there's a derivative, and then there's a del mu of this variation of the field. Okay, under the symmetry transformation. And then it's the same exercise. You can take this and write it as a total derivative. Okay, this is a total derivative. And if you write it as a total derivative, then it will be epsilon times this this object here, this part plus the derivative acting on here, this clearly is the Euler-Lagrange's equation of motion for this field xi. Okay, and therefore this can be set to 0. Okay, this can be set to 0 because this is the Euler-Lagrange equation, and therefore the variation in the Lagrangian density, because of the change of the way this is a transformation of the Lagrangian density, okay, which happens because the fields transform in a given way, is given by this expression here, epsilon times this expression. But as we saw that this Lagrangian variation must also be equal to, this variation must be equal to a total derivative of some object, let's say this object I, script I, okay, and then therefore so this, if you like, should be equal to this. So if you like, right, this should be equal to this, and if this is equal to this one should be equal to this, and if this is equal, then you see what we have here, we have this expression here. Okay, we have this expression, and you can take this on one side of the equation, and you can say that there should exist a quantity for which del mu of this quantity is equal to 0. Okay, so here, mind you, this del xi appears, which we know completely. It's not some arbitrary variation. It's a known variation under the symmetry transformation. Okay, so therefore, this is known. This is known. If we know the Lagrangian density, this part is known. This is known. If we know the Lagrangian density, we also know this. So all this is known quantities. All these are known quantities. But this generally proves that there exists a combination of the known quantities for which the divergence is going to be equal to 0. That means this current is going to be conserved. There's going to be a conserved quantity that one can write in terms of the field degrees of freedom. Okay, so this demonstrates the fact, whenever there is a continuous symmetry under which the fields transform, there has to be a conserved current, a local expression of something being conserved. Okay, that has to be there. Okay, whenever there is a conserved, whenever there is a continuous symmetry. Okay, so this J mu I can define as this object within the bracket here, as I have done. Oh, again I have made a mistake here. Yeah, so I've dropped a delta psi here. Okay, that has to be there. Okay, so this equation, this is the statement of Noether's theorem. Okay. Now I must say that there's a better way to do this. Okay, there's a better way to do this. Again, which I don't think I can get into a discussion here. But essentially, what is done is you take this parameters, okay, whatever this transformation is, and you try to make them like local functions of space and time, and in the process, you basically gauge the symmetry. This is called gauging the symmetry, and then vary with respect to the gauge field to get the conserved current. Okay, so then that gives us a procedure of weakly gauging without introducing any dynamical term for the gauge field, and we can do that. That is like a slightly advanced procedure. If you don't understand, I just wanted to mention it, but if you forget about it. I mean, here I don't think we can explain all the nitty-gritty details of that, but that is like a super easy exercise. Here you have to use all this complicated formula, but that is like a super easy exercise with which you can find out what the corresponding current is. Okay. So all I'm saying is there's something easier than this, but more conceptually difficult. Okay, so algebraically much easier, but slightly more conceptually difficult to grasp. That's why I'm not getting into that discussion. Okay, so now let's take the example of translation, which is our main goal. So if we take the example of translation, the coordinates are transformed in this way. Okay, so if the coordinates are transformed in this way, then the fields are transformed in this way. And as I said, this is analogous to the so this is for this particular symmetry. This is analogous to the variation, this thing. In the earlier discussion, I had assumed that there can be any continuous symmetry, but now I am assuming that the particular continuous symmetry is this translation, where this parameter is some infinitesimal parameter, mu, and then it is very clear that the fields must transform in this particular way, okay, whatever the fields are. So if it transforms in this particular way, then we can perform the same thing, that now we want to write down L, and we want to say that L is also a function of x. So the L also must transform in the same way as the fields. Okay. So, the fields transform in this way. If you think of the L's as a function of x, then it also must transform in the same way, where the variation is this is some del mu L. Okay. Now, I have used a slight trick here. This a mu del mu, this I'm writing as a nu, but I'm introducing a Kronecker delta mu nu del mu. Okay, you will see the reason why I'm doing that very soon. So, there's the index here, I'm keeping this a phi index nu, and it's not contracted with this del mu here. Okay, it's just contracted with something inside and not this del mu. Okay, so very good. So that's the thing that, I want to keep it at. So once I do that, this object is, my the one that I was calling I mu, but there are 4 parameters. So this contains another index corresponding to which parameter you're talking about. Okay, this object is the one that I was calling the I parameter, the script I parameter in the previous general discussion. Okay, very good. So now this delta xi is also del mu xi, as I mentioned. Now let's just use the formula that we derived very generally. We can show that, a nu, of course, this is outside this parameter. For every parameter, we have one index here. So a mu contracted with this index. Okay. Why is that? Because this variation, for every a nu, there is a del mu xi. Okay. This new index is for every a mu. Okay. Okay. So maybe here I can write this as, I don't know if that's a good notation. This variation for every a nu. So this is the new index which is there, which is del mu xi. Okay. Then this new index must contract with this del mu xi here, and the j mu remains as it is, but the mu index contracts with the a index here for every parameter here. Okay. So essentially what I'm doing, I'm just using this formula that we had found, but this formula we have found for 1 epsilon, right? But now we have like 4 such epsilons. So this gets an index here and an index here. Okay, that's all, I'm saying. Very good. So there are 4 such equations. Corresponding to every symmetry, there's a conservation statement. And translations is like 4 coordinates, you can translate. So there are four such equations. Okay. So very good. Now, so we can define whatever appears inside as the current. And so this object, T mu nu, is this object here for translation. So whatever is the Lagrangian density, we know all the terms. I can perform this differentiation, and this is the Lagrangian density. Then this is the corresponding object that is manifestly conserved as a consequence of space-time translational invariance. Okay. The object that is conserved like this is referred to as the energy momentum tensor. In fact, this formula is something which is called the canonical form of the energy momentum tensor. Okay, it's called the canonical form of the energy momentum tensor. And as you know very well, that if you take this and write it out, so there are 4 such things, 4 such equations. So I'm just, for nu equal to 0 and the spatial versions, okay, Imj is 1, 2, 3. Okay, then I can write it as 2 equations. This is the time equation and this is the space equation. Okay, so the time equation, this would have the interpretation of a conservation of energy equation. Okay, and this object, if you integrate it over the space, gives you the total energy of the corresponding configuration. Okay, and this object here, T0j, this, if you integrate it over space, you get the momentum in the field. So we are talking about field theory. And this, as you know, this formula determines everything in terms of the field degrees of freedom. Okay, so it's a local quantity which determines everything in terms of the field degrees of freedom. So from this so-called energy momentum tensor, we can read off the energy density and the momentum density and then integrate them to get the energy and the momentum of the fields, okay, in a particular configuration. And if you remember, then this object here is basically the energy current density, and this is the momentum current density, okay, and these are the particular component of this covariant energy momentum tensor, okay, so they are also there. So just as an example, you might want to take this simple theory for the scalar field and find what is the corresponding conserved energy momentum tensor for the scalar field. So I've just used this formula here, okay, and you can check whether this is my correct expression for the energy and momentum for the scalar field. Okay, I would like you to note that this is automatically T mu nu is equal to T nu mu. Okay, it's automatic because you can exchange it here. Eta mu nu is symmetric here. So basically, this object is this object that you find here, the canonical energy momentum tensor for this particular theory is automatically symmetric under a mu nu exchange. Okay, so here there was one more step, I think. Yeah, so here this gives me T mu upper, nu lower, and there's a delta here. So if I want to, let's say, bring down this mu index, I have to multiply with a eta, right? And that eta will multiply this this object here, and the delta and eta multiplied, because this is like an identity multiplied with the eta matrix. So that is going to give me a eta only. Okay, so this eta comes from there by lowering, from the lowering of this mu. Okay, good. Now it's time for Maxwell's theory. So this is my Maxwell's Lagrangian density. Aha, what am I doing? There's a minus sign here, so minus half. Again, I'm writing this in this particular form. Now I can use the formula here. So if I use the formula here, this term becomes minus f mu nu. You see, there's a del mu of this object, and this xi essentially is my three components of my A vector, A alpha. Okay, that's what I have. So basically, when I do this differentiation, I get f mu alpha here when I do this differentiation. And again, this differentiation, I get a factor of 2 here because it can act on this f or on this f. So I get a factor of 2 that takes care of this. The sign remains, but I have a f mu alpha here. Okay, I have a f, because I have a f mu alpha, that should be contracted with this quantity here. Okay, this quantity is del nu, is this new quantity which is here. But this object is the same thing as this object here. Okay, therefore this alpha index is the same thing as this alpha index here. Okay, I hope this point is clear. Okay, because this differentiation I did with del mu A alpha. So this A alpha should be the same A alpha here. Okay, so that's the idea. So this is the structure of this term, and then this L is directly the full Lagrangian. So this minus sign becomes plus 1/4 of f squared. Okay, that's what we have here. Okay, delta mu nu. And if we bring it down, then this is a mu alpha, mu A alpha. So this has to be like like a lower index and upper index because there is a contraction, and this also has to be lower and upper because there is a contraction. But this eta mu nu comes because I have to, while lowering, I have to multiply with the eta mu nu and get this delta lowered. Okay, so that's this mu index. If you want to lower, then I will get a eta mu nu. Okay, so that's because I have to multiply with the eta mu nu on both sides to get that done, and this is what it is. Okay, so this is the energy momentum tensor, it seems, for the electromagnetism. Okay, or just Maxwell's equation without sources. This seems to be the energy momentum tensor, but there's an immediate problem with it. I have claimed that the energy momentum tensor is a very physical quantity. It relates to energy, momentum, energy current, momentum current, etc. But you see, this object, as we have found the canonical form, so this is the so-called canonical form, canonical, because I am using Noether's procedure and this formula. So this is the canonical energy momentum tensor. Okay, so now we can just take that we can just take this canonical energy momentum tensor and look at it. So if you see this, then we'll find that there's a term like this, which is clearly not gauge invariant. Okay, this is clearly not gauge invariant, and neither is it symmetric with the two indices mu and nu. Okay, now both are problems. So this is a problem clearly because physical things cannot be gauge cannot depend on which gauge you are giving the description, because physical things should be gauge invariant, because our description cannot depend on our gauge choice. Okay, that's just a redundancy. So it's not a physical symmetry, it's a redundancy. So our physical objects cannot depend on our gauge choice. Okay, it has to be gauge invariant. So this is a problem that we have a gauge non-invariant energy momentum tensor, at least the canonical form is, and also it is a problem that it is not symmetric with the two indices, between the two indices, exchange of the two indices. Okay, clearly if you exchange mu and nu, okay, you get a very different term, and this term is not symmetric. Okay, so now why is the second thing a problem? Why is if you write down a energy momentum tensor which is not symmetric, why is this a problem? Okay, to understand that, we have to understand, there's a corresponding angular momentum density that one can define out of the energy momentum tensor, and that has to be a conserved quantity. Okay, that has to be a conserved quantity, and you define the angular momentum density in this way, that you take, beta and gamma, and you take anti-symmetrized beta and gamma in this way, as I've written it here. Okay, so if you like, this is some version of if you like, when I define angular momentum, let's say xi xj, the 3D version. Okay, there was a xi xj, I wrote down xi pj xj pi, and then took this object and contracted with an epsilon to get what is angular momentum, right? This is what we did for particles in 3 dimensions. Okay. Now for fields in 4 space-time dimensions, covariant way to do it, is to do this thing, that you take the energy momentum and you basically take this is taking like a 4 cross product. Okay, this is like taking a 4 cross product with x. Okay, the x coordinate. Okay, so if you do that, you get an object with 3 indices. Okay, now how should you think of this object with 3 indices? I'm calling it angular momentum density. But what I really mean, you should think of this object as like the full current. Okay, so what I mean is, if you take this object and if you consider the time part of it, right, so here I have mentioned, okay, so this object has the same status as the full current. Okay, so if I take the time part of it and integrate, then I get what I would call angular momentum. So the time component is the real angular momentum density, and the space components are the angular momentum current density. Okay, that's the way in which you should think of it. And if you take the angular momentum, which you get after integrating the angular momentum density, which is the time component, then this angular momentum is same in status. Like if you take momentum and x for a particle, okay, for a 4 particle, if you take this, and if you anti-symmetrize this alpha and beta indices like this, then you get the corresponding angular momentum for the 4 particle. Okay, where this is the 4 momentum, and this is the 4 coordinates, x and p. Okay, then you define, this is for a particle. This is not for a field. For a field, you do this. For a particle, 4 particle, you can do this. Okay, and so you see this m alpha beta essentially has 2 anti-symmetric indices. It's anti-symmetric because of the way in which it's anti-symmetric in these 2 indices. So there are 6 independent m alpha beta, if I divide in this way, and this corresponds to the 3 boost and 3 rotation symmetries. Okay, this is the this is the symmetry corresponding to Lorentz transformation, if you like. Okay, so so mi alpha beta is the corresponding angular momentum current density. Okay, so this as you know, angular momentum, when we are discussing it, angular momentum is a conserved current corresponding to rotations. So that in the general case, becomes there are like 6 objects like that which are conserved, and those 6 objects are essentially corresponds to, again, symmetry statements. And this is, I'm not demonstrating that here, but you can try to demonstrate it also. But again, for this course, I don't think we can, there's need to go into all that. But this is the idea. Okay, but you see, if this is defined in this way, then what happens is if we say that this has to be a conserved current, this is a conserved current, then this is a conserved current provided the energy momentum tensor is symmetric. Okay, that is a requirement for angular momentum to be a conserved current. Okay, how is that true? Because I take this and plug in the definition here, and when I take the del alpha, then there are two terms where the alpha acts on the stress tensor, and that gives me 0 because even the canonical form of the stress tensor is conserved. That is the idea, right? But then I have these two terms where there's alpha, del alpha which acts here, and there's a del alpha which acts on here, and that gives me T gamma beta minus T beta gamma. Okay, and if this is not 0, then the angular momentum would not be conserved. So the stress tensor has to be symmetric if there's a angular momentum conservation, has to be there. Okay, and that also has to be there. Okay, so I mean, essentially, this is all, if you like, all these, rotations, translations, and all these are part of a coordinate symmetry, like symmetry of the change of coordinates, and therefore all their information is contained within this conservation of energy momentum tensor and its symmetry of the two indices. Okay, so therefore we have a problem. Both these things, it's not gauge invariant and it is not symmetric in the two indices. Both of these are problems. Okay, now how to address that problem? Okay, the way to address that problem is to first observe the following thing, that if we take this canonical stress tensor, then we can add to it some lambda mu nu, where this lambda mu nu itself is divergence vanishes. Okay, so I can take a quantity whose divergence vanishes and I can add it to the stress tensor. Okay, then I will get a new quantity which is, if you like, a modified stress tensor. Okay, and this modified energy momentum tensor, so this is the energy momentum tensor, sorry, and this modified energy momentum tensor would also have a conservation statement, because if I take a del mu on this, del mu on T mu nu is 0 because this is the canonical stress tensor, and this is by choice. I'm adding a term so that it's del mu. This thing is 0. So therefore, del mu theta mu nu is also 0. It's guaranteed. Its conservation is guaranteed. So I'm free to add to the canonical stress tensor. I'm free to add terms whose divergence vanishes. Okay, that I can do. Okay, and even then, so terms like these are called improvement terms, and then I have a improved stress tensor. So I can use this fact to remove these two problems, that the stress tensor is gauge not invariant and it's not symmetric. That thing I can remove by using the non-uniqueness of the energy momentum tensor by this quantity. I can use this fact to remove it. Of course, this non-uniqueness is going to remain. Even if you remove it, this non-uniqueness is going to remain. But I'll have a comment to make about that. It's the stress tensor is. It's not true that the stress tensor is not unique. Okay, it's uniquely fixed. But this is a procedure. There's a procedure to improve the stress tensor and to convert it from the canonical form, which is the problematic form, to some form theta mu nu, which is gauge invariant as well as it's symmetric in both the indices. Okay, so let's see how it goes. So we can choose some improvement term. We want to do that, and for that, notice this is the expression that we had for the energy momentum tensor. So let us take this, because we want to make it gauge invariant. Let us write this in terms of the f. Okay, so this term I can take, and I've written it in terms of the f. Okay, and then I have taken it and substituted it here. Okay, so there's one term where this f has been contracted with this object, and there's this term which I have written outside. Okay, this term is f mu alpha del alpha a mu. Okay, this is a term which is additional. Okay, and this term within the bracket is clearly gauge invariant because it's written in terms of f. It's also clearly symmetric, because if you exchange this is the same object. It's clearly symmetric. Mu nu is already symmetric. So this is also symmetric, and this thing. So what about this additional term that we have? So if we take the divergence of this additional term, then we see that there are two terms. The first term, vanishes by the equation of motion, del mu f mu nu alpha. This is the equation of motion for this particular Lagrangian density. Okay, so that term vanishes because this Lagrangian density is for without sources we have considered, and this term vanishes. And then so this mu then hits this one. Then as you can see, this is symmetric and this is antisymmetric and it's contracted. So this term must also be equal to 0. So this whole thing vanishes. So this additional term that is left over, once you just minimally make this quantity gauge invariant, okay, this is a term which is whose divergence vanishes. So we can choose our lambda. So this term, with the minus sign, we can choose our lambda so that this is cancelled out. So we can take that stress tensor, the energy momentum tensor, and we can improve it by removing this term which is divergence free, and even then this should be conserved. Okay, and even then this should be conserved. So basically this is what we do. This is equal to 0. This is equal, the del mu of this is equal to 0, we have shown. But now so this lambda is chosen this way, and we can also see that this lambda is not only lambda is not only how should I say, it's not only a object whose divergence vanishes, but also this is a object which is a total derivative, because you can pull the derivative outside, and when the derivative acts on f mu nu, it vanishes because of equation of motion. So you can pull the derivative outside, and this is itself is a quantity which is a total derivative by itself. Okay, so therefore after making this, choosing this improvement term, our energy momentum tensor takes this form. Okay, this is not the canonical form, this is the improved form, but it is symmetric under mu and nu exchange, and it is gauge invariant. Okay, so this is going to be the energy momentum, the conserved energy momentum tensor that will be there for electromagnetism. Okay, after this improvement. Okay, so here I have a comment. So basically about the uniqueness. Okay, so there's a procedure of finding the energy momentum tensor by varying the Lagrangian density with respect to a background metric which is fluctuating. Okay, so you can take the theory and put it on a manifold which is not Minkowski spacetime, but something more complicated than that, and you take a metric and you vary it. You vary the metric. Okay, so the metric here we know is fixed to be eta mu nu, but you can take this metric and vary with respect to the metric itself. Okay, if you do that, then you get this, whatever you get is basically the energy momentum tensor. You can define it that way. And if you do that, you see symmetry is automatic because mu nu exchange, the metric is symmetric. So, by the symmetry of the metric, the energy momentum tensor conservation, that just, the energy momentum tensor is symmetric, that just follows. Okay, and so you might wonder, this also tells us that this kind of, you will do this. This is again going to take us beyond the, that's why I didn't get into the details of it. Whatever I have described to you is a canonical way of doing it, and it's a completely well-defined way to do it. But this is again a more simpler and more sleek way, which defines the energy momentum tensor uniquely. There's no room for it anymore. You can define the energy momentum, conserved energy momentum tensor uniquely, and it is also this energy form of the energy momentum tensor that appears in the Einstein's equation. Because again, for Einstein's equation, you write down a Lagrangian and vary with respect to metric, and then the Einstein tensor must be equal to some energy momentum tensor, okay, of the matter, and that is precisely which sources the Einstein equation. Okay, this energy momentum tensor. Okay, but then again, when you do a GR course, when you do a GR course, you will learn all about it, and therefore, I'm not getting into the details of this. Okay, so finally, I would like to leave you with this exercise of taking the components of this and writing it out in terms of the E and B fields. Okay, so this I'm leaving as an exercise. You might want to do this. I'm sure you might take a guess, right? You might take a guess of what the answer might be, right? You might be able to guess what the answer might be, because you know that these are the energy, these are the statement of energy conservation and momentum conservation, and you are already familiar with, what is the energy and momentum. So you see, you know that the T naught naught would probably go as E square plus B square. Okay, maybe there's a c squared. Again, there's some proportionality constant, and then E I0. Is right. So right. So E0I, which is the momentum density. So this is let me say, okay, first let me write E0, right. Let me write first EI0. Okay, this is the energy current. Okay, this, as you know, is the Poynting vector given by E cross B, right? The ith component of that. Okay, similarly, you will have the, this is the answer to this exercise that I've asked you to do. I'm just writing it schematically. And then energy, and then energy, right, and then energy, if you take this and try to write the, if you take this and try to write the, what you call is the momentum density, right? Momentum density. This is also density, right? The energy current density. Okay, that is 0I, and that is also E cross B, as you know very well. Okay, and this fact, you see, follows from the fact that the energy momentum is symmetric. I0 is equal to 0I, because that we have implemented, because we wanted angular momentum to be conserved. Okay, and that essentially, because of angular momentum conservation and the symmetry of the stress tensor, the indices are symmetric. Therefore, we saw that there was this coincidence that whatever was momentum, whatever was energy current density, it was the same thing as the energy momentum density. Okay, so that that just follows from this fact that this energy momentum tensor has to be symmetric. Okay, that's there's a deeper reason why that is the case. And similarly, that's the final thing. As you can guess, the Tij, that should come out to be the components of the Maxwell's. This should be the Maxwell stress tensor, right? Right. So you should be able to show that these things come out in terms of the components. So you have to demonstrate this by using, you know what is F in terms of the electric and magnetic fields, and plug it in here and demonstrate that this is the case. Okay, and all of this, the conservation, energy conservation equation, that just, is the conservation, it can be simply stated in the relativistically covariant way as del mu theta mu nu equal to 0. Okay, it's as simple a statement as this. Okay, all right. So this is more or less whatever I want to discuss about the Lagrangian formulation of field theory. So as you can see that we understood how to write down the Lagrangian of how to constrain the Lagrangian of electrodynamics on symmetry grounds, and then we understood how to derive the equation of motion out of it. We understood if there is a charged particle, how to write down its Lagrangian and try to derive the Lorentz force out of it. And then we understood Noether's procedure, and with help of Noether's procedure, we are able to write down energy momentum conservation equation, which corresponds to translation in space-time. Okay, so that's more or less what we have discussed in this video. Okay, so I will just stop here. Thanks a lot for your attention. Yeah.